Right. So the first thing I want to discuss with you is just to review a bit why the standard model came to the decision of uh, naming the electron as a dimensionless point and charge. We have to review this to understand also a bit more from my research. So when you say what is the size of the electron, you have different options, which we will see later on. They are conflicting each other. So the first thing, if you ask a physicist what is the size of the electron inside the bound electron inside the atom, and a canonical answer will be that there is no size for the electron. It's just the expansion of the wave function of the electron inside the atom, the orbital, the electron orbital. So in that case, the first option we have for the size of the electron is to the Bohr radius. So it's about 10 to the power of minus 10 meters. So that's one option we have to say about the size of the electron, right? But then we have a second option. If we regard the electron as a ball, a filled ball, because the sphere is empty inside, but the ball is just something which is compact, it's filled, a curved circle. So if we have the option, we say for one who thinks that the free electron now, not inside the atom, is some kind of small condensed energy ball, and this can be constructed from bits of charge. We can have bits of charge, and we try to compress them together because they are all negative, the same charge. They will repel each other. So when we try to compress this charge, it gets harder and harder to compress for a given radius. So the energy can be here, this energy here, yeah. The energy we need to compress the charge of the electron in a given radius r is given by this equation here. It's E squared 4 pi, the permittivity of free space times the radius. So if you do this calculation using also the Einstein's equations and make this equation here, then we get about 10 to the power of minus 15 meters. So this is the second option we have. It's an answer. So this is actually the classical radius. The exact values is 2.81 times 10 power of minus 15 meters. And that was fine and dandy until the year 1925, where Ubelchek, the two Hollands, the Ubelchek and what is the other name? Ubelchek and Goodsmith. Goodsmith, yes. In 1925, they have discovered, the electron has also a spin. It's behaves like a small bar magnet, and so it has a magnetic moment. So that was a problem because now, if you want to calculate what is the radius for this magnetic moment, you can go here in this equation. This is a semi-classical equation. Here is the G factor, which is the Dirac factor times 2. Okay, we don't calculate any anomalous magnetic moment, just the Dirac function magnetic moment. So if you do here, this is the angular momentum of because the Goldsmith and Ubelchek said that it's actually physically spinning, so it has an angular momentum. So this is the angular momentum. This is the radius, the electron charge, the G factor, which is equal with 2. And we know that the magnetic moment of the electron is 1 Bohr magneton. So if you put the tangential velocity here, the tangential velocity, if you put it, equalize it with the light of speed in the vacuum, the radius, which only this can hold, is the reduced Compton wavelength. It's the wavelength divided by 2 pi, it's radius actually, and it's 3.86 times 10 over power minus 13. So this now gives a larger radius for the electron. That's a problem because the classical radius, as you remember here, is power of minus 15. But the Compton radius gives a radius of a radius of minus 13 meters. So it's larger. So you cannot have a smaller radius like that, because then you don't get the correct value for the magnetic Bohr magneton, which is the magnetic moment of the spin magnetic moment of the electron. Yeah, is it fine? Okay, can you hear me? Is it okay?
Yeah, very good.
So that's a problem. So that's another conflict. So you have the classical radius, which gives minus 15 meters, and then you have the counter radius, because exactly the electron has a spin, which says the electron cannot have a radius less than minus 15 meters, because then you have to go to superluminous speed. Yeah, you have to then go to superluminous speed in order to get for a smaller radius, to get the same value of the Bohr magnet, the magnetic moment of the electron. You have to essentially increase the speed here. The charge is fixed, invariant. The G factor is invariant, so there's no go. So actually, this radius here, which is called the reduced Compton radius, which is the Compton radius divided by 2 pi, is the minimum allowable radius for the electron in order to fulfill its magnetic moment value. Yeah.
Yeah.
Okay. Then we say, okay, you have the Compton radius, and then you say you have also the empiricist view, the experimenters. So what you say if you're an experimenter? So when we say experimenter, there are actually, I know, two ways they try to measure some size for the electron. The one is the electric dipole moment of the electron. But we will discuss this later. There's a problem. So this is the charge of the electron. And assuming that the electron is asymmetric, yes, so it will not a perfect sphere in general. Okay, and then what they do, they measure the interaction field, because this is a charge, this is the E field. They measure the field here on the spin axis. But that's also the fine point here I have to make. They don't measure overall the sphericity of the charge, but only on the spin axis. So they say if it have, say here is the north pole of the electron, if it has a hump, it must have an electric dipole moment, because it's anisotropy, you know. But so far there are two experiments. The latest was the ACME 2 experiment at 2000 back at 2018, and they had put an upper limit at 10 power of minus 30 meters. They cannot find any anisotropy. You see? So one of the conclusions was, since we cannot find one anisotropy, that means two things. Either the electron is perfect spherical, or the electron is less than 10, the cross section is less than 10 power minus 13. Can you see my cursor here?
Yeah.
Can you see the cursor? Okay, good. So I repeat, because they couldn't find any electric dipole moment, they say either the electron is perfect spherical, or, like a second conclusion, the electron must be smaller than 10 minus 13. But what is the point here? The first observation we have to do is they measure only the sphericity on the spin axis. That means if it has the electron has a hole here, and it has exactly equal and symmetrical hole here, they will not find an electric dipole moment. Even if it's in total not homogeneous, it can have a hole here or a hump here and a hump here, but they measure only on the spin axis. So if the anomalies, the defects are equal and opposite, they will not find any electric dipole moment. That's a problem. That's a problem. Yeah, and we will discuss this later, because I have some from our research here in the university. We have to make some suggestions of how should these experiments conducted in the future from a theoretical point of view. So this is the first method. The other method is the measurement of the anomalous magnetic moment of the electron. I'm sure you have heard the exciting news last year about a discrepancy between the theoretical model and the actual measurements for 4 sigma, 4.2 sigma, I think was the discrepancy. And this method concludes they put an upper limit in the size of the electron. The upper limit means the maximum size it can have, at 10 power minus 18 meters. So this is another conflict. So the empirical people say we cannot find any size. We have the option, this is option of 4. We have option 3, which is derived from the spin of the electron about the radius. We have, according to its mass and energy, the energy of the electron, we have another classical radius, it's minus 15. The spin radius is minus 13. The experimentalists cannot find any sides down to the 10 minus 30, the one group, the one type of measurement, and 10 minus 18, the other group. So the other option is, what the heck? They say, we don't care about the physicality of the electron. We just make it a mathematical point and work on from there with mathematics. So that's okay. That's fine and dandy. But the problem is you can have some information. You can missing some if you don't have a physical model. You may miss some important information which will progress the knowledge and understanding in physics. So this is not actually, they put the problem under the rug, to talk bluntly. Yeah. So we have now to conclude about all these things, since they're all conflicting. We have to assume that first the electron has shape. If we assume the electron has a shape, that's a manifold. I don't know, mathematically it's not 100% correct. Manifold means much more things, but let's, for the lack of a better word, let's call it shape or manifold. Yeah. So if we assume that the electron has a shape, therefore a manifold, and also a size, then its manifold shape must be more complex than a sphere or a ball. So a sphere is empty inside, but a ball it's actually a sphere with filled interior. Yeah. So, and also it must be dynamic. The geometry of this manifold, of this charge manifold, is not just just a sphere, but it must be more complex and also must be dynamic. So that means it can actually increase in size and also shrink in size. It must have some elasticity. Yes, elasticity. So, and the most important thing here is this here. What about let's say maybe it has all the above options together. So in first glance, you say it's not possible. How you can have all the options, all the above options, except of course the dimensionless point options, option 5. How this shape can have all this together? The classical radius, the Compton radius, which is the spin radius, actually the charge radius, and also when the experimentalists don't try to see any sides, they cannot find any sides. How can this all the options in the same time? That's a problem. So how is this possible? Okay. So έχω meeting. Γεια σας, έχω meeting. Sorry for the interruption. I'm still in the university, and the guard came here and checked on me.
No problem.
Okay, I'm in my lab actually. So let's go and see now. Just go straight to the model without any technicalities. I'm sure you have read you have seen the video presentation, which is with the more technical version, and I'm speaking exclusively on the model there and how it was constructed and how it was derived analytically and also simulated So I will not very much focus on that. I just want to talk about the implications. So let's see the final slide here of the whole of the paper actually, which is the model. So the model here is it's actually like a solenoid which has spirals and the flux goes straight inside homogeneous field. So, but here the spirals are on the sphere. We have spirals on the sphere. We have actually two vortices, and here we have the known phenomenon. It's actually in nature also. If you have two water vortices called modons, and they have the turn in the opposite directions. When they come close together, they create a vortex tube here. They're actually joined with a vortex tube. We will see that later on the slide. So you have some this you can call it a coaxial dipole vortex. So here this horn tube here, it came out from we don't want it. It was not fitting. There was no fitting done. It came out actually after we measured the model the dimensions. This here, believe it or not, the diameter of this small tube here came out exactly exactly, not exactly on the fourth or on the fifth decimal point, but at least at the first three decimal points, it came exactly the classical radius. So the diameter here of the horn tube is the classical radius, and this from the center to the equator here came out the reduced Compton wavelength. And we know from theory, this is not my equation, it's actually in the literature, that the fine structure constant, and it's actually it's a bit ironic why they call it fine structure constant, because it's exactly the fine structure constant of the electron. This ratio determines the whole geometry of the manifold, of the charge manifold. So we know that the fine structure constant is the classical radius divided by the reduced Compton wavelength. They knew this equation, but they didn't have. There was no geometric meaning on this, because they regarded. If you regard the electron as a dimensionless point, of course you cannot study it geometrically. It's a dimensionless point. It's over. End of story. But we did a bold move and gave volume and manifold and shape on the electron, and then we saw actually the physical origin here of the fine structure constant, which is a geometrical proportionality constant. It's the radius of this divided by the radius of the equator, and this is the fine structure constant. The fine structure constant, as you know from Schwinger equation, the first loop contribution is the fine structure constant divided by 2 pi. So the fine structure constant determines also the G factor, therefore also the anomalous magnetic moment of the electron, and this is controlled from these two radii here. So this was actually, I believe, an important realization. We have here how the model turns. So I don't know if the animation is you can see the animation or it's jerky. Is it okay? Is the animation okay?
Yeah, it's fine. It's good.
Yeah, okay. So we have first to clarify some things. Yeah. What are these lines? What kind of substance is this? Because you know the charge of the electron is not the same as the electrical and the magnetic field. These are actually the interaction fields of the charge. The charge generates an electric and a magnetic field, but we cannot say it's the same. It's just the E and M fields are the interaction fields of the charge of the electron with its environment. Yeah. So what are these lines? So you must. It's very important to understand, in order to understand our research, but that we regard that this is electromagnetic flux. It's nothing different. It's no some exotic type of energy or ether I mean, it could be a disturbance in the ether field, but the disturbance in the ether field, for people who believe for the ether, including me, I admit, yes, but not in the sense of the ether of the old one, of the absolute plane. I believe in a Maxwell ether, which is dynamic, yes. So if you disturb the ether or the time space time, the distortion manifests as electromagnetic flux. In our research, the electromagnetic flux is more fundamental than the electron itself. It's the strings by which all particles are woven. So in our research, we see the electromagnetic flux as more fundamental than the particle itself, because it's not the electron does not make the electromagnetic flux. The electromagnetic flux makes the electron. It's a dipole vortex on the ether, you know. So that's very important to understand in our research. So I mean, it may sound awkward to some people, but everything we believe is a distortion of space-time. So everything, all matter is some kind of condensation of the space-time. I don't believe that the notion about space-time being empty or vacuum space being empty. Nobelist Wilczek actually said that believes on the materiality of the vacuum. So the vacuum can be some kind of medium, which all the defects and distortions of the mediums manifest in our reality as gravity or electromagnetic flux and so on. So electromagnetic flux is very important to our research. Okay, so now we are fine with that, but there is a problem. There's a problem here because the experimentalists cannot see this radius here. It's 3, which is 3.86 minus 13 meters. They cannot. They say no, it's much smaller. It's much smaller. But remember, when the electron is inside an atom, it gets the orbital distance. So we can also assume that the electron has some elasticity. When it's inside it's inside the radius, the atom, it expands to occupy the orbital radius, the given orbital radius. What happens if let's assume that the translational motion of the electron has some effect. So this is also important. You see here is the two vortices, water vortices, which when you put food coloring inside, you get a tube here. So it's the same topology, but now it's in a 2D version. And this is stable. It gets in water. And then when you look more closely, you have here an isotropic formation, which actually creates here isotropic distortion. So this is actually an analogous of the E field created by the charge. It's an analogy here. So we can, yeah, where is it? Okay, shrinking last. Yeah, what is the problem here? Yeah, we have to see also this. This is a hydrogen atom. So we have here the nucleus, one proton, it's a hydrogen one, and this is the wave function of the one electron. So the wave function in our model is the flux of the electron. The charge manifold of the electron is the wave function. And if you have, I'm sure you know that the electron, in the wave function, the probability wave function, it says that it spends the most of the time inside the nucleus. You can read, I can give you reference, which this is a probability function. It's not actually a probability function. We say, no, it's physical. It's the manifold, the charge manifold of the electron, which you don't have the opportunity to investigate because you say that the electron is dimensionless point. So here is not a dimensionless point. Here, the charge electron has a manifold, and therefore this charge manifold is the wave function. So it says that because here the lines are more dense, the charge is more dense here, that's equals, it's analogous to a probability of the electron being more time inside the nucleus. So the red here is the nucleus, and this is the one electron, the wave function of the electron. So yes, sorry. So yeah, let's continue. So there's a problem here. If you reduce here the radius and say go minus 18 meters, then we have to go to superluminous speed. So that's why they say no. The standard model said no. It's a dimensionless point, and it has intrinsic spin. So it's another word of saying we don't know what the heck is going on. It has a quantum spin, but it's not a classical spin, but it has angular momentum. That's the funny thing. So you have classical angular momentum, but it's not created by actual spin. That's what the standard model says. We don't say this. We say no, it's actually spinning. It has the Compton. It has the Compton radius. This is the radius. But what happens? Why the experimentalists cannot probe the electron? Why they cannot measure any cross section for the electron? We believe from our research also that the charge, the manifold of the electron is elastic, has elasticity. You know, it can shrink under some conditions we will discuss now, and it can also expand inside as a bound electron inside the atom, and shrink when in translational motion. Because these experiments are done under speed, they give a translational motion to the electron. We believe that the electron shrinks. Besides any relativistic effects, it can actually move with, I don't know, with 30% of the speed of light or so. Or it will have also some relativistic Lorentz contraction and time dilation effects. But besides that, we believe that inside the frame of the reference frame of the electron, this manifold shrinks when it's not in translational motion, because these equations are actually for the stationary electron. You know, this equation are for, so it is possible that this magnetic moment here is not invariant. I mean, the G factor is invariant, but it's possible that during flight, when it's inside the beam in the accelerator in the cyclotron, it's possible that the magnetic moment is not invariant, and therefore you can have you are not restricted by the given value, by the rest value, and can lower, and then you can go, of course, to smaller radius. It's not a problem without breaking any speed limit of light. I have written to 3 professors, and I have made in physics tax exchange a question. This same question: are you sure that during flight inside the cyclotron, the magnetic moment is invariant and does not change? I didn't get any answer. Nothing. Niche. Nothing. Even in the comments, it's now the thread is now 1 month there. Usually, because I'm in physics stack exchange, I have a high score there, and I think I'm 2% of the most active visitors there. So I should get an answer, but I did. I always ask something, and I always get an answer from experts there. But for this question, they don't really have an answer for this. So it's not sure that we are restricted for a fixed value of the Bohr magneton. It could be that inside the beam, when it accelerates, it shrinks. So that will allow the whole manifold to shrink, and that's why, because all the experiments are high energy experiments, that's why they cannot find any size for the electron when they measure it. The second thing is that a free electron is very difficult to measure because it has elastic scattering. It's not like the quark, which is inside the proton, and the proton has an elastic scattering, so you can bombard it with photons. Here, if you try to bombard a free electron with photons, it will fly away, just fly away. So what they do, they try to some kind of its bond inside an atom. They will try to some loose kind of experiment, but it's very difficult to do a penning trap experiment with a low energy experiment with a penning trap. It's difficult. So yes, so what we can do now? What is the thing? First, this is actually a paper I'm now trying to write and to publish using our model here. So what we can do? Let's see the first measurement they try to do. They try to measure the electron by measuring the electric dipole moment. Yeah, but according to our research, our model, they will never find any electric dipole moment because these two holes are exactly symmetrical. So there is no difference. What they have to do, and that is our suggestion from our research, is not just to measure anisotropy on the spin axis. You know what they do? They just put a vertical magnetic external field. The electrons are lying on the field, and then they try with some methods to find an anisotropy here. But as I said before, if if it's very spherical, they will not find any anisotropy, or that's our contribution, or if the defect here is exactly the same with the defect on the south pole. They will never measure any kind of electric dipole moment. Currently, they're planning the next year to go to measure with a sensitivity of 10 minus 31 electrocentimeters. It's a weird unit, but you can call it 10 minus 31 centimeters. 10 power minus. So they went to extreme small sizes, and they cannot find it. And our model reveals that yes, you cannot find it because you just measure here on the spin axis. No, you have to compare this with others. There must be some kind of toroidal electric moment. So this here, this hole here, creates here the radius at the equator is larger, and this missing here curvature is the anomalous magnetic moment. That gives the excessive geomagnetic rotation because it's not a total sphere now. It's missing a small part, and our research is the missing part is exactly the classical radius of the electron. So the missing part of the curvature of the surface here is the classical radius of the electron. And yeah, this is the Schrödinger equation, which is you see here is the fine structure constant divided by 2p. This is the first loop contribution. But we have derived a second equation, which now everything binds together. The classical radius of the electron, the Compton radius, which is the charge radius of the equator, the fine structure constant, and now everything binds together with our model with this equation here, which is the classical radius is the anomalous magnetic moments times the Compton wavelength. So that's extraordinary because you see the Compton radius is this here. The Compton wavelength, it's divided by 2 pi. Yeah, where's the Schrödinger equation? The Schrödinger equation. Sorry. Where is the Schrödinger equation? Yeah, okay. There. So it's 2 pi. Sorry. Yeah, okay. So it's the classical radius, and this is the reduced Compton wavelength. But the Compton wavelength is the reduced Compton wavelength is L, which is the Compton wavelength. The normal, they're 2 pi. So it's actually a circumference divided by 2 pi. It's a radius. So this is the radius, the reduced Compton. But the Compton wavelength in our manifold, in our model, is the circumference. The circumference is the normal Compton wavelength, 2.42 power minus 12 meters, and the radius is divided by 2 pi, which is the reduced Compton wavelength. And we have here this equation derived that the anomalous magnetic moment is actually times the Compton wavelength is the classical radius, which if you analyze it is the missing part here, which is responsible because now it's not a perfect sphere. It's not a 2 pi r sphere, is actually causing the anomalous magnetic moment of the electron because it's missing this part here and here on the south pole. So this creates the first loop contribution, this geometry defect here, the two vortices, the pole vortice, the two holes in the dipole vortex creating the anomalous magnetic moment. So we actually suggested here, there's also another possibility. There's the possibility that we will never be able to measure any anomaly in the electric field, any anisotropy. It will be perfect spherical because we have this example in nature where you have this dipole, the two joint dipole vortices in the water, but they create this as anisotropic because you have spirals. But here you see the field, the electric field, the interaction field is perfect spherical. So there's a problem. And what they try to do is to go inside. This is the far field. They try to reach the near field, but because the the elastic scattering, it's very difficult to go near the near field, so they cannot find the anisotropy. So the experiment we propose here to do, actually, you will read it. I hope this paper will be published in 1-2 minutes. I think I have also something put as a preprint in ResearchGate. You can search it there. I think it's my newest preprint. So you have here a magnetic field and an electrostatic field, and you have here you introduce an electron, but with very small velocity, not very fast, inside the field, and you get here a Lorentz interaction, the Lorentz force, and then you try, you keep fixed here the magnetic field, and you try to vary the electric field, and you rotate the whole apparatus here, and try to find an anomaly on the sphericity on the far field. No, you cannot go near the charge, but at least you can. Now you will have a chance to measure the whole sphericity of the electron, not what they do. They just do what the people in ACME do. They just measure the anisotropy here on the spin axis. We recommend to measure the full sphericity around the unit circle, 360 degrees, not just here. They will not find any anisotropy. In our research, we have calculated that there is actually an anisotropy, an electric dipole moment, but not between the two poles, but between each pole with the equator, because this is not a perfect sphere. And we have calculated here, so the classical radius is it's minus 15 meters, but because here is the nearest, the most narrow part of the tube, but because you have the funnel here, I think we have calculated here a value of a prediction. That's a prediction of our model. No, this is the classical radius. It's larger than this. It's sorry for that. Yeah, it's this here. It's 18.2 minus 15 centimeters. So it's minus 17 meters. The amount of anisotropy they're looking. But remember, they're looking at the range of minus 30 centimeters. We say no. The anisotropy is much larger, but you just look in the wrong place. Not don't compare only the two poles on the axis. Compare each pole with equator. So yeah, that's the newest development. The newest paper we're writing now with my PhD advisor, Professor Donidakis. So Yeah, I mean, I finished. I don't want to add anything else. I don't want to spend more of your time. I don't want to go to the very technical details. These are the emulations of the model we did with Wolfram Alpha. Just only 2 points, maybe, because this idea about the dipole vortex here and the coaxial is really not something totally new. Actually, Dirac, when he said about the magnetic monopoles, you remember that even Dirac actually says that there are not actually real uh, magnetic monopoles, but there are two vortices, two distortions in space, a monopole and an anti-monopole, which are connected with a Dirac string, which is infinite thing and long, and that's why we cannot see it and we cannot measure it, and that's the magnetic monopole. So imagine now a universe. I'm not saying necessarily the Big Bang, because I know some people don't believe in Big Bang. Actually, me also, I'm skeptic about the whole thing, Big Bang. But anyway, somehow they must have created the first particles must have been created. So you have firstly a very homogeneous substance field, and then it cools off, and there are some vortices are forming, some defects in the homogeneity of the medium. So imagine uh, after the creation or whatever you call it, this you have two anti-rotating with different angular sign of rotation clockwise and anti-clockwise, and when the close together, then this Dirac string is created. So now imagine that these two together come here and connect. So this is actually the electron are two magnetic monopoles. So our research says that the magnetic monopoles were right under our nose. Of course, there are no magnetic monopoles free in nature, but they are hidden inside the electron. Yeah, actually, the electron are two a magnetic monopole and a magnetic anti-monopole joined together with this uh, vortex tube here. So the analogous phenomenon we have in nature, which is it's 18, I think. Yeah, yeah. So I don't know if you can see it here. There's actually a video, a very nice video from Physics Girl about. It's called. You can search it. It's called crazy vortex pools, crazy pool vortices, something like that. So I don't know if it's very clear here, but sorry. No, not this here. Sorry. 18, 18, 18, yeah. Yeah. Okay. You have here a vortex on the water on the surface, and you have a different. This say here is clockwise, and this is anti-clockwise. When then they put some food color in here, and you can see here the same effect. Only this is the two version of our model. If you try to compress it, then in a coaxial fashion, then you have the model. Uh, yes. Okay, so this is the magnetic moment. The flux going inside here is the magnetic moment, and the spiraling charge on the surface is the electric charge. And these two fields are unified now. This actually is the cause why the electric and magnetic field are interchangeable, because they are entangled inside its manifold. The manifold, the electric and magnetic field are unified inside the same manifold. So that's actually you have the electric and the magnetic entanglement, which are inside inside the charge of the electron. So this is the electron actually. This we call actually the electron. There's nothing, and it's a confinement of charge, at the center you have the center of mass, right? So you have the mass here, exactly where the classical radius is. Remember, the classical radius is derived from the mass equation, yes? So the classical radius is there where the mass is concentrated, at the center of the manifold here. And of course, it has a center point, a geometrical and mathematical point, which you know the center of mass is anyway a dimensionless point. So you can connect the dots. So I think I have, yeah, 57 is another I want to show you. Sorry guys, maybe you are tired. It will take no more than 10 minutes. 10 minutes. I want 10 minutes more. Is that fine with you? Yeah.
It's very interesting.
Okay. So this is the standard model, which is the dimensionless point, so nothing. So we inflate here this here are the two interaction fields, the electric fields, because it's charge minus the vectors are going inside, and this is the magnetic, the magnetic field of the electron, the spin magnetic field. Yes, but these are the interaction fields. We don't now we don't talk about this here. We talk about this yellow here, the charge, which is an unknown. Nobody knows what is going inside the charge. It's forbidden by the standard model. You are not allowed to investigate the intrinsic mechanics of inside the charge. So, but we say no. We make the bold movement and we will investigate. So this is a very nice animation. You have the Einstein equation of the confined energy here. If you use the parallel axis theorem, you can derive the angular momentum of the electron here. Yes, MVR. The tangential velocity is the speed of light here. So you have here the magnetic moment, the charge around your electron. So the chirality of the electron is to the left, it's left-handed, and the intrinsic chirality, and this here is the positron. Anything else from here? No. So 58. Okay, that's also a very important conclusion from our research. When you put the electron in a z-axis field, it will start geomagnetically rotate its magnetic moment around the beta vector here, the b vector, yeah? But what is not very known is that this angle here, which is 54.7, is fixed. When you increase the strength, it will rotate faster. Yeah, the frequency, the gyro frequency will increase. But this angle here is fixed. It's fixed, and it can get only two values: plus 44.7, and when you inverse the field and spawns down, minus 44.7 degrees. So this actually is the source of the quantization of the magnetic moment of the electron from the Stern-Gerlach experiment. We have also a preprint about which we talk more about this specific subject. Because this angle is fixed, it can get only two values, plus 45.7 and minus 45.7. That exactly makes the quantization of spin in space of the electron. The quantization of the magnetic moment of the electron in space. So this angle is a magic angle. It's not. We don't coin this name here. This is a mathematical term. It's actually arctan square root of 2. Christopher will. I'm sure he will know about this. This angle. It has to do something with conservation of energy. I'm not sure. It's a most efficient angle, and nature used this angle. So we have then made I don't want to go to this discussion here. We have this. We have to translate the angular momentum of the electron and all of its characteristics in the geometry of the manifold, and these were the equations we used. And then we have the parametric equations for the Horn torus. It's in the set Mathematica. Sorry, Wolfram. if you go to Wolfram Mathematica, you will see the equations for the Horn torus, but the Horn torus is it has not the high, it's not sphere, so we have to put a deformation factor here on the equations to give it the exact, to make it a spheroid. So then we actually analytically also calculated the model, but then we ran it with a simulation and found three candidates which fulfilled both the angular momentum criteria and the speed of light. We should not exceed the speed of light, and the angular velocity, the angular momentum should be the non-angular momentum for the electron. So we have found this candidate here to be the most very good approximation. So the angular momentum is 0.045, and the simulation gave out 0.755. Notice here, this is not the angular momentum on the z-axis, which is, of course, half. This is the total of the mass angular momentum. It's in all three axes, x, y, z, which is known. It's square root of 3 divided by 2. So yeah. So this is the total angular momentum. Yeah, not to be confused. And then we, after we finished the model, we started to make here some measurements, and we found this astonishing fact that that this here is coincides with the classical radius. This is the Compton radius, and the fine structure constant, which this explains the physical origin of the fine structure constant, which is really actually the fine structure constant of the electron. So sorry for you if I stretch it a bit. I don't know the time. I don't know how long I'm talking now. Oh, it's 1 hour exactly.
Yeah, exactly.
A bit, yeah. So thank you very much, and yeah. Maybe just sorry, because this is also important.
Wonderful.
This is also important because we have to say something about that. Yeah, sorry about that. So the most important, also one of the most astonishing facts we were able to theorize is the charge of the electrons is made from one photon actually, and so what's going on here? You know the Compton radius. So the Compton radius is topologically a spin 1 particle will have a circular motion, a perfect circle. That's why it's exactly h, the angular momentum, because it's the most efficient rotation. It produces the highest angular momentum h than any other kind of motion. The circular rotation is the most efficient angular momentum generating motion. So, but the electron has 0.86. Remember it's square root of 3 divided by 2 h bar. So it's what this tells us that it's actually a twisted loop. It's not a perfect circular. It's a twisted angular momentum created by a twisted loop, and we were able to calculate exactly this. And what it came out, not to confuse you with many details, that the whole electromagnetosphere of the electron is created by just one photon, which is, but it's a photon. You know what happens? It's a photon which is not just translating in space. It's a twisted photon. It's not a circular loop. It's a twisted, and it's spinning also. So it's spinning around an axis and also revolving, and that gives the angular momentum. And because this is spinning with the speed of light, it creates the whole electromagnetosphere of the charge of the electron. So it's just one photon. And if the simulation gave us exactly this wavelength here, the golden the candidate, the third candidate was the golden ratio candidate, because we found out, believe it or not, that the golden ratio is the best deformation factor to get the characteristics of the electron. So it calculated exactly 3.86, which is the Compton radius. So when you this twisted ripple, if you unfold it and stretch it, you get exactly the Compton radius here, the Compton wavelength, which is I believe it's quite astonishing. And remember, when two in an electron positron pair annihilation, what you get? You get only two photons. Why two? Why photons? And remember, the photons have exactly the Compton wavelength. So our take, what we think it's happening when the electron and the positron clash together. These two photons got unbound, get free, and then extend in space and become a normal photon here, become a normal photon and fly away. So this ripple, when the positron and the electron annihilate, they get freed out, they get knocked out from the electron, from the volume of the electron, they expand and become a photon, and then they fly away. I mean, why should it could it could decay in something else, but why it decays always at two photons? For me, it strongly infers that actually that the electron is a twisted spinning photon. That's what is my hypothesis, my speculation. But it's not just a speculation. It's more than that because we have a model and we have calculations. And if you want to see this more. Okay. Sorry, I'm finished from here. Just last animation. Okay. So this here is the the spinning photon, which spins very fast relativistically and creates the whole magnetosphere. And it has also the Dirac belt characteristic. So the phase becomes always after 4 pi of rotation. This comes again up. Only after 2 pi rotation, this is down. Only if you have 4 pi of rotation, it becomes in the same state. You have the problem with all the fermions. It's not like a classical sphere where you rotate it. If you rotate 360 degrees, it will come to the same point. The electron must have 4 pi rotations to go to the same state. And this is actually measured with neutrons. It's actually an experiment which is done. So it's confirmed that it's 4 pi. But our model explains also this, because if you watch carefully, only after 4 pi of rotation, this here becomes exactly on the same state, which means it's like a pretzel, It's going up and this goes down. Yeah. Let me say something. I don't know. I have something else. Maybe. Yeah, maybe here something interesting. I guess. Here. I guess, yeah. Let's visualize it. What I mean with one photon creating the whole charge of the electron of one twisted spinning photon. So you have here, you have the twisted photon ripple. This is the revolution it makes. This is the horizontal spin, and this is the superposition of both. So it revolves and spins also. And this is the final product. You see, this is the volume of the manifold, and you have here the photon which is spinning and revolving very fast, and because this is done with relativistic speeds, it creates the whole charge. This is charge of the electron. It's 8.66 the reduced Planck constant in all x, y, z coordinates. Yes, that's all. So stop sharing.
Okay, great.
Oh, great presentation.
Yeah.
Fantastic.
Awesome.
Yeah.
So
Awesome.
There's a lot in there was a lot in that as well, especially on such a small subject as the electron.
It's a universe. The electron by itself is a universe alone. If Dirac has this problem, many scientists have this problem. Actually, there's a famous saying from Fermi, I believe, that before I die, I want to die, and the devil tell me what the electron exactly is. I think Fermi said that, yeah, Pauli Fermi, that the first questions I make to the devil when I go to it will be what the electron is. So it's a very hard subject.
Yeah.
And it's good to make predictions, and I agree with the standard model, and it's the amazing theory and all that. But what I believe is that it doesn't give all the answers, and I see I see a tendency to go outside, new particles. No. You must go inside. No, I mean that in the last 50 years, that's what people did. They went to smaller and smaller sizes to find something new. They didn't go out. Now they say, no, it's an elementary particle. It has nothing in. It has no structure. And we look outside in the vacuum for new particles. No. We have to learn. We have many unknowns. We have much to learn when we go inside. We have to make intrinsic mechanics of the. But they don't like it because what's the problem? I'll tell you what the problem is. The problem is when you measure statistically, even statistically doesn't matter because you have systemic errors and you have to repeat it. You get always the same charge. You get always the same magnetic moment for the electron at rest. Yeah. So what does this mean? It cannot be a probabilistic function. The intrinsic mechanics of the electron must be deterministic. That's the problem with these people. They don't want to go back to deterministic. In my opinion, the electron works like a clockwork. It cannot be nothing else. It cannot be probabilistic. Because if it would be probabilistic, you will not measure the physical properties of the electron will not come always after statistical analysis the same. It's not possible. But okay, that's my opinion. I believe because my model is classical. As you know, it's just geometry and it's a classical model. So yes, the interaction between the particles is probabilistic. Probably yes, because the Heisenberg asserted the principle. Maybe because also it's kind of stochastic system, chaotic. I don't know what, and we cannot predict all the interactions. That's kind of fine and dandy. But inside the electron, it cannot be probabilistic. It's impossible. And actually, Hooft, one of the Nobel Prize winners, has also the same view that the particles inside must be deterministic. The mechanics, the intrinsic mechanics, must be some kind of clockwork.
Well, does that imply then that size has nothing to do with probability? You know, we often think of this idea that the smaller you get, you enter into a new world with the new rules that are probabilistic. But
yes,
it sounds like you're saying you can go even smaller again, and you still have determination in there. So it's an interesting perspective.
And the problem I found with because I didn't know, I thought that I was very amazed about these experiments. They measure the sphericity, but then I realized after reading about 6 papers and watching 2 presentations, 2 lectures of I think Cornell, something like that, that they just measure on the axis the anisotropy. They don't bother to go.
Yeah, interesting. The z-axis is very important, isn't it, in quantum mechanics?
Well, this here is a horn torus. I don't know if you can see it.
Yeah.
It's a toroflex, actually. It's a catcher. So if they measure here and here only on the axis, they don't measure the whole sphericity of the field, of the far field.
Yeah.
If this defect is exactly the same with the other, they will not find any dipole moment. Never, ever. That's my point.
Ah, okay.
And, I don't know. I thought they were. I thought they were more sophisticated, but no. Because then I conducted one of this, and he was very kind to answer to me. And I told him, do you check for dipole moment and also in other on the unit circle and in the other direction? No, we check only because we have an external field and pin the magnetic moment of the electron inside the external field, and then we measure with methods the electric dipole moment in the direction of the spin axis, not around. And I told him, why you don't try to measure also? And he told me, no, theory does standard model does not predict any quadrupole. That was his answer. That the standard model does not predict any quadrupole. But then I told him, yes, but did you actually verify it experimentally? No. So they're more dogmatic on the dogmatic. They don't try things out. They say
Yeah.
no. The theory says no. So why we should check there? We check only on that.
Yes, interesting. I wonder, do you guys want to take like a 10-minute break and
Yeah.
then come back for questions?
Yes, yeah, you can for questionnaire, of course.
Okay,
yes.
brilliant. I might kick off some questions. I got some. I'd say some pretty hard questions and probably some very easy questions.
No, now it's 11:30 here. It's almost midnight.
Oh, okay.
Not many amateur questions.
Okay, well, we'll see how we go. You know, whatever answer you can give is perfectly acceptable. I'm not, okay. So what did we? I just want to first of all, beautiful graphics, amazing looking, and
yes,
I think
the animations were made from Wolfram Daimler.
Yeah,
It's in the paper. He came actually and visited me here. This first 3 to 3rd to 6th of June, he came here in Crete and visited me, and he's very nice person, a good person. He's 75, 76 years old.
Who is this? Not Stephen Wolfram.
Sorry, I said Wolfram. No, it's Wolfgang Daimler.
Wolfgang.
Oh, okay. And is he connected with the Wolfram Alpha project, or?
No. Just
okay.
My tongue just.
Sorry, I might have zoned out there. I was thinking of so you created some of the graphics on Wolfram Alpha though,
yes, the simulations, of course. Simulations are from but the animations are made from Daimler.
Oh, okay. Sorry,
because the simulations are different. Simulations have to input the parametric, the polar equations, and then the simulator puts out the trajectories. Actually, it calculates the path integral, some kind of path integral, because we needed this perimeter to verify the model. So yeah, the Wolfram Alpha simulation makes the manifold when you from the equations you input in. But the animations are different. The animations are not exact, are just illustrations,
Yeah.
Yeah. I mean, they use math, but they are not exact because you cannot visualize this small,
Oh, absolutely, yeah. I see. So, I mean, I watched your previous, I watched the video presentation you did. I nearly think the presentation you did tonight was even better. I suppose there was a lot more visuals and equations, and because you're there as well, we can see you. It made it.
Yes, I thought it's wrong to start and say, forget whatever the other people did. I will now go and make this. You have to study what their thinking was, what was the history. Because when you don't get history, you are lost. You have to do this kind of investigation, research.
Yeah, I think one of the first things that struck me about your original thing, the idea of the clockwork interior being deterministic, therefore classical. I thought that was a nice bit of logic. So we also discussed that there just after the.
Yes, I mean I don't know. I'm not very good in probabilistic mathematics. I mean, in the pure because you tell me, can you have the exact specific values just by the probabilistic? I mean, you could, yeah, you could. But it's not nice. It's not, interaction is nice. I believe quantum mechanics is very good if you have two particles or more, but it's not good for describing the physics of the one particle. It's very good
Okay.
if you have interaction with particles. Yeah, it's good. It makes prediction. Okay, it's an effective theory. It doesn't claim that this is actually what is happening physically. I respect that, but besides the predictions and the mathematics, the physical interpretation is terrible. I mean, you have so many interpretations. The Copenhagen interpretation, it's terrible. The interpretation, and then other thing I want to say, they have this strange thing of describing the physical electron. They say it's a combination of a left-handed electron with a right-handed electron. And then I said, and they're in superposition and they're alternating and all this stuff.
Yeah.
This is nothing else. Just if you see my model, you have the spirals going left-handed in the South Pole and right-handed in the North Pole, or whatever else.
Yeah.
So if you look, if you see the manifold, you get this superposition between a left-handed flux with a right-handed. So then I realized that all this story with the left-handed electron there is just describing the manifold, the wave function. It's actually the charge model of my fiber model. So that's
Well,
and the problem is, of course, you have to recite to very difficult explanations and mathematics if you say that the particles are dimensionless. You cannot describe it physically. If you say it's dimensionless, you lost all your description power. Then you have, of course, to recite to some complex explanations with mathematics, which are, however, totally disconnected from physics. That's
yeah.
not a physics explanation. I like mathematics. It's a very, very nice tool, but I think somewhere we rely too much to mathematics. We should rely more to physics.
Yeah, that makes sense. I like that logic as well. Like
And and,
you
and,
have
and
to look.
physics without a picture, a shape, it's no physics. Physics needs an object. If you don't have an object, something. No.
Yeah, absolutely. Yeah, I was saying that I like that the logic about looking outside the electron for like the physical shape that you're talking about makes a lot of sense, obviously. And I'm glad you brought up the chirality spin superposition thing, because I was wondering about that a bit. If the left and right superposition is correct, then how does it collapse into like a right or a left particle when measured, or does it? Does that make sense from an
Yes.
experimental point of view?
So, what makes you sure that it collapses only in one or of the two?
Okay, because you were saying that it's alternating between left and right. So if you were to, like, I don't know, maybe perform an experiment that measured it as left, that's only just in that instance.
Yes, but Christopher, I believe you mean the helicity. The helicity is something how it turns when it translates in space. I'm not talking now about this. You mean maybe you mean
Oh, okay.
it collapses. The helicity is how it turns clockwise or anti-clockwise when it translates in space. Chirality is something else.
Okay.
Chirality is independent of relativistic motion. So I can,
Yeah, because well, like I suppose it becomes more complicated again when you bring bosons into it, doesn't it? Because then when you talk about helicity with bosons, it's something
yes,
else, or compared to like chirality.
it's very complicated. Yes, I believe. I believe. Can I share a bit? Can
Yeah,
share
go
you
ahead.
something?
Yeah, I think you still have. Yeah, I mean, if you could give a few maybe brief definitions
Yes.
of those terms, like might be
Yes.
handy.
Just a minute to prepare something here. Mm,
But is it not true? Maybe this might clarify where I'm coming from. You know how there are
yeah,
no
just a moment, just a minute more, just a minute.
well, yeah.
So
Well, I mean, yeah. Is it okay? Like, I'll wait. I'll hang on
yeah,
for.
I'm almost ready, almost ready.
Okay, no problem.
So so you have a share. Yeah, that's good. And this. So you see my screen, yeah?
Yep, yep.
Okay. So what we have in our model as chirality, as intrinsic chirality, which then dictates also all the other things. We found, of course, we are not 100% sure. Yeah, I mean that's what the model shows, but I'm not saying that this is. But we have a very good theory about that. Um, so chirality, you see here in the electron. This is the electron it has a minus sign. The G factor has a minus sign. So that means that because the negative charge, the magnetic moment is anti-parallel to the spin axis. So this here is a spin down. If you put your right hand and go to as it turns here, then your thumb points down. So this is a spin down electron, and the theory says that the magnetic moment is anti-parallel, so it's in the other direction. So this is a spin down electron, minus one half spin number, and this here is a spin up. And because the spin vector is up and this has a negative charge, the magnetic moment vector is pointing down. It's always anti-parallel. Whereas in the positron, which has a positive charge, spin axis and magnetic moment are aligned. So this is spin up, and both spin axis and the magnetic moment south north is pointing in the same direction. So what they describe as ER and E left. I have actually a print also in the research kit. If you look, say you here up here, yeah, and you look down on the North Pole, what you see? So let's say I cannot remember now. This is the North Pole and this is the South Pole. As you look it from up and down, yeah. So you see here this flux lines here of the manifold, which are darker. But behind this, you see the fader lines coming from the opposite pole. Yeah, it's transparent. So that exactly what they mean. This is a right-handed, the flux going this way, and when you see the opposite side, they're going to the other direction. They're leaning in the other direction. So this is that's exactly what they're saying. That the physical electron consists of two electrons, a left-handed and a right-handed chirality. So here you see the one electron, the left-handed, and the right-handed from the other side. And the same also, but vice versa now for when you view the manifold from the south pole. So, and now they say that they alternate, when you choose here a point in space, you will see that it alternates between the darker line and the darker flux line and the softer, the lighter on the background. So this actually, these lines are in superposition. So what I'm saying is that, and actually this is also what the standard model is, that there's actually one electron. It's a physical electron. Um, there are no two electrons. It's just the manifold, one viewed from one pole to another. That's all. What I suspect you asking me, if it collides, they have a way to see if it, at the moment of the collapse, if it ends up left-handed or right-handed. Yeah, is that maybe your question? At
Yeah.
the moment it collapses, why it turns out left-handed or right-handed? I mean, at the time of the measurement, that's all the whole thing.
Yes.
By collapse, you mean measurement.
Yeah, exactly.
So yeah, okay. I never thought about it, but I think it's obvious because when this thing collapses, it will end up on the measured apparatus in one of the two sides. Yes or no?
Yeah, that's what I'm thinking. Yeah.
It can either be this side or either this side. It cannot,
Okay.
cannot land both at the time of the measurement with the same side,
Okay.
with both sides. Maybe that's the physical meaning of why it measures left-handed or right-handed. And the other important thing, is that this chirality is intrinsic, but it's also inherent. Inherent, the chirality dictates also the helicity. You know, the helicity depends on the chirality.
Oh, okay. Yeah. Well, because I know from what I understand with helicity, it seems like you're talking about it being a translational thing. That's interesting. But also,
Yes, because,
if you look at helicity from one side, it's the opposite. As like if you see it from the front, it's opposite it.
Exactly.
From the back.
Exactly. And helicity also is relativistic. It's prone to relativistic effects.
Oh, yeah.
Imagine yourself catching up with an electron, and then going to overtake it, and then you will see the helicity to turn around, to go opposite, because you see it's a relativistic effect. You will see the turn going the other way around when you overtake it.
Yeah. So that kind of looks like, because this is.
Yes,
it depends like what you're describing here, though, because you're looking at it from the north and the south pole, and you have different helicities.
Yes, when it's traveling, but you talk me about when it's collapsing. When it's collapsing, yes. It will end up either with this side or the other side.
Okay, yeah, that's a fair point. Another thing that
yes.
You know this idea of the left-handed fermions and right-handed anti-fermions. So, you know, you can't have a left-handed fermion or a right-handed anti-fermion. So, from that point of view, it sounds like this left and right thing is sort of an intrinsic property that is like not always in shift, but somehow, you know, like a thing that the particle carries along with it sometimes. Like it's a steady state, constant thing.
It's important what you measure and how you measure it.
But would you think so? So how would you handle that? Would you say that
it's something? Maybe you will be now astonished with this point. Why the magic angle? That was I never explained in the presentation, which is very important. Why? Yes. Why the magic angle? Because it has to do with this thing, with the helicity. So why the magic angle? Sorry. Can you see me now?
Oh yeah. If you stop sharing your screen, it should come back.
But I have to. I show you just one more slide, and then I stop sharing.
Oh yeah, no, keep going. Yeah, no. If you need to keep sharing, yeah, go ahead.
Yeah.
Yeah, we can.
So the question is, because now you have prompted me to answer this. It's actually an observation.
See.
Yes, here. This. So, it's in Greek here. Yeah.
Yes.
So you remember this slide here about this magic angle which comes up and it's fixed.
Yep.
You can get only two values, plus and minus this value here. You can actually check it up. If you put Wikipedia magic angle, it will come up. So it's angle which is it's like a fine structure constant. We observe it all the time in nature and also in particle physics. So this angle is why this value? So can you see why this value here is? Why this value? Why not something different?
Yeah.
What causes this value here? So I tell you now. You remember that the flux is in a solenoid. You have spirals, and then you got you get the straight magnetic flux, the homogeneous field inside the, well, quite homogeneous inside the solenoid, yeah? So here you have spirals on a sphere. These are actually spiraling, it's vortexing, and you have the straight flux inside, which is the magnetic moment of the electron. When you see exactly at the equator, when you measure the model, you will see that it has the magic angle incorporated inside. So the angle here, the tangential, which is passing exactly at the equator, at the moment where the line is passing here, to the z-axis is exactly 54.7.
Wow.
So now here's the important part. When you put the electron in a z-axis external field, you have a z line here of the external field. What happens if you have a screw and you try to screw it, to twist it in a pole, in a straight pole?
It's down.
Yeah, it starts to leaning. Exactly, it will start to leaning. It starts to lean as in the angle which it has the spiraling, the spirals of the screw. You know this angle here.
Ah, yes.
This angle here dictates also the angle here.
Yeah.
You have here the pole.
Yeah.
You screw here, and you try to turn it around. This straight pole. It will exactly align here with this angle, which is dictated by this inclination here. So the flux lines are coming here with exactly this angle here is to the vertical is 54.7. That is exactly the reason why you have the quantization of the magnetic moment in space, because it can take only two values.
Yeah.
Up 44 degrees, and if it's if the external field is reversed, it will go the other way, minus 54.7.
Right.
So that's a very important observation from our model. I mean, it comes also it computes very nicely, and it comes very nice out. So it must be true. I don't know.
Yeah.
Maybe I'm wrong. I don't know.
So that angle there of the 54.7 degrees, is that it's different to the 0.866?
Yes, the 0 point is the angular momentum. But the electron.
Yeah.
Maybe it's better this way here. So in the z-axis, when you put the electron in the external magnetic field, John can explain this better than me. If you put the electron in the z-axis magnetic field, external field, it will start rotate its magnetic moment around the z-axis.
Yeah.
This is the Larmor frequency. It's called geomagnetic rotation of the magnetic moment of the electron. Yeah.
Yeah.
So, and the geomagnetic rotation is gamma times the B field, the strength of the field B times the geomagnetic ratio. Yeah. So the stronger the field is, the B field, the faster is the rotation. 2 Tesla, 3 Tesla will rotate faster. But what is not very known in the literature, you have to dig very, very hard in, is that this magic angle is always the same. It doesn't change with the strength of magnetic field. So you have here, this here is a spin-up electron. It has on the z-axis half. The h bar is actually units of angular momentum. Well, it's joules times seconds, but it's actually angular momentum. Yeah.
Yeah.
The Planck constant. So in the z-axis, it's half. That's all we know. But what we don't know, which is less known, is that the electron has also an angular momentum in 3 axes. It's not just in one. X, Y, Z. The angular momentum in the X, Y, Z in the Euclidean space is not 1/2. It's 0.866, which means what it means is this: that you have the known on the z-axis angular momentum, it's half h bar. You have the magic angle. You know this here.
Yeah.
You know this from the literature. And so you can calculate the x component of the angular momentum, the total angular momentum, which comes out very nicely. It's the reciprocate of square root h bar. It's 1 divided by square root of 2 h bar. So it's 0.7, you know. But this here now, this is the problem. This is not allowed by the Heisenberg uncertainty because you can examine only one axis at a time. You cannot superposition the vectors here.
Yeah.
But what we're saying is no, forget we now examine the intrinsic mechanics. I don't care about quantum mechanics anymore.
Yeah.
I'm now inside the electron, and where quantum now has no grasp on me. So I'm allowed to do this. That's what I'm saying. Otherwise, if we were outside the electron and examining the you know the normal, not the intrinsic mechanics of the electron, but the normal, the outside interaction of the particles, you are not allowed to do this. You're not allowed.
Yeah, well, I think part of the reason why I'm a bit confused, or just from all of this information, is that it looks like here you're equating 0.866 to the magic angle, and
yes, it's all bind together. It's actually it's not it's square root of 3 divided by 2 h Planck, but it's approximate 0.866 Planck. Yes. If you have this is known, the angle is known.
Yeah.
This is known from the literature. It's called the total mass angular method, which is in all the Euclidean space, not just in the z-axis, but x, y, z. Actually, this here you can actually say it's the xy plane, but for simplicity reasons, we just say the x-axis.
Oh, okay.
Yeah, you can also say it's the xy plane here.
But
then it gets more complicated. So if you know this, our model used this here, this angle, this, and this are known, and then calculated this, which is the revolution. And this makes
So the way to get the magic angle, though, is like arctan.
Arctan squared 2.
Squared 2. Yes, then the way to get the, let's say, the other angle, the 0.866 is...
That's not an angle. That's the amplitude of the vector.
Oh, okay.
This is the amplitude of the vector. So this actually is...
okay.
Yes. Tan A, the magic angle, gives the two angular momentum, which is the revolution. You know, you have one rotation here and one rotation here. And then you combine the rotation and superposition. So this is the total angular momentum. This is the spin angular momentum. Imagine the sphere rotating on the equator. And this is the revolution. It's actually the ripple, the effective rotation on the z-axis. The ripple makes inside the manifold. The photon ripple I showed you before. So this must equal square. Tan A is this yes this here divided by this, and this must be square 2.
Yeah, because another way you can get that figure is to just the sine of 45 degrees, and then to get the other one, the blue vector.
Yes, of course.
Take the cos of 45 degrees.
Yes, of course, yes. But I mean, we calculate this. This is not known. This is in our theory. It's not allowed outside the intrinsic world of the charge. These three were known. We not invented this. This is known. This is known in the literature, and the magic angle is as well.
Yeah.
But the quantum mechanics does not allow this here.
Yeah.
But we don't do now quantum mechanics. We are doing intrinsic mechanics of the electron. So I can do that.
Yeah, interesting. Yeah. So, well, I was just wondering then, going back to the left-handed, right-handed antifermions and fermions, how would your model eliminate left-handed fermions or right-handed antifermions? Is it able to distinguish between them?
So our theory, because you
So is this going more into like weak?
Yes, I can actually think about it and write a paper about a preprint, but I didn't thought it because we keep to try to keep our model as simple as possible. So we say, it does not translate in space because we want to be as fundamental as possible. So we freeze it in space. It doesn't translate in space. It doesn't move linearly in space. It just spins there. And also, we say it's a free electron and it's totally, completely isolated from the environment. So there's no other interaction. Just the charge, the self-confined charge. That's all. We didn't examine the external fields, the E field and the interaction fields of the charge, the E field or the M field. Maybe another time, but not not this time. So yes, that's an interesting question, actually.
Right.
Uh,
Yeah.
yes. So how you can you repeat again the question? How you distinguish?
Yeah.
Uh,
So with the weak force is able to distinguish between like a left-handed fermion and a
yes,
and an
only the weak force. Yes, yes.
so will you be able to
So
distinguish that
so
fermion?
let's think about the weak force. What is the weak force? What weak force is actually electromagnetic phenomenon, but in very short distances inside the nucleus. So it's less than 10 minus 15 centimeters. So it's actually, and this is called electroweak.
Hmm.
So it's actually there's nothing different, but only the distances are shorter. So uh, the weak force distinguishes between the left and right. Yeah, it sounds okay for me. Why not? Why should it not distinguish?
Hmm.
Because when you go, uh, you are in a planet and you're far away. You cannot see the futures. The classical electromagnetism is not inside the nucleus; it's macroscopic. It's more far away. When you go when you now go inside the nucleus, you go very closer to a planet, and you start seeing the futures. And now it matters if the flux is coming left-handed or right-handed. It's a matter of range, I believe. I don't know if you understand me, if I was clear.
Hmm.
Uh, Classical electromagnetism is far away, is the far away fields. And the ranges are much more than minus 15 centimeters. Electroweak force just studies the decay of the particles to other particles as they transform from one to the other. Yeah. So electroweak force, all the actions are taken in a very short range,
Yeah.
which is the range where the effects are taking is now comparable to the actual sides, assuming they have sides. So now it becomes significant what is the manifold, the exact manifold, if it's right-handed or left-handed.
Okay.
I mean that's what I just a quick thought. I never really thought about it, but
Sure.
I believe it's a matter of distances. It's like increasing the resolution. If you see a ball which has very small thin lines engraved from a long distance, you will not that will not matter. But if you start go closer, then it matters. And because all the experiments, when done in close range, in the nucleus range, then the experiments, the measurements are very close to the sizes, and then they can distinguish the left from the right interaction.
Yeah, that's interesting. So
I mean, imagine it like two small balls colliding, and then the balls have engraved lines, and then they collide again. Maybe there's another interaction in close range, but it will not change the long range interaction, which is electromagnetism. But in close range, because you will see the lines they interact, then the direction there is different. You can see there a different interaction, some more detail in the direction. So you see the two poles colliding and going apart, boing. But when you see close enough, you will see that they also twist a bit because that's what the experiments are doing. They're kind of microscope. The higher energy the beam is, the more they can probe smaller and smaller distances. So it's again something about measurement.
Okay.
Resolution of measurement.
So yeah, so I was thinking, you know the way you have F4, so F sub or and F sub S, which is the spin and the rotation, was it?
Yes, Fs is the spin. But, I mean, I could use rods, but I hate rods. I don't like it. So I convert everything in hertz.
Cool.
So
Yeah.
Fs is the spin rotation and of the ribbon, and Fr is the revolution. But the revolution, the spin rotation is a circle, but the revolution is not a circle. It's twisted. So we have to do Wolfram alpha to calculate the angular momentum from the irregular rotation. It's not a regular rotation. It's twisted. No.
Yeah. Okay, that clears that up. I was just a bit confused. So you talk about how the model can how would you say, well, accurately model, I guess, spin one half in terms of rotating once, or it has to rotate twice before it gets back. So that's
the Dirac belt, yeah.
Right. So, but if you were to take the how do you say, the horn torus, and if you were to like stretch it out so it's like an ordinary torus, and you had the loops on that, I think it would be kind of maybe easier to see what you mean if you were to rotate that and have it spinning and revolving at the same time. You'd be able to see. So it seems to me, like in my mind anyway, that because it was very difficult to like pick a point on the ribbon and follow it along. So if the ribbon,
I can show you something else.
Great, yeah.
I have to share the screen, of course.
Oh, you're still sharing, so it's okay.
Yeah.
But yeah. So like, if the ribbon was different colors, it would be easier to see. Or...
Yes, I agree. But the man, the Daimler did without payment. Just I cannot ask the man to do this and this. He done all the animations free. Generous. It was So I cannot force him and make also demands. I'm not that kind of.
I would say that if he's capable of doing that, he's probably able to put some colors on a ribbon easily enough. But I don't know, because
but now it's over. It's over, Christopher. I don't want anymore to bother. He's a good friend. I don't know. He's 78, 76 years old. So he actually has a physics degree. A bachelor degree. He has a background in physics, yes. So he has also a page in ResearchGate. He's in research. If you put Wolfgang Daimler, you'll be fine.
Oh, yeah. Yes. Okay.
Yeah. And he's more in infinities and mathematical physics.
Cool.
Yes, I wrote a paper here. Just a moment to find it.
Yeah.
This it will become very obvious what I mean. Just a moment.
But would it be fair to say then, in order for that to work, that the F4 would have to be twice the speed of Fs? In order.
Yes.
It does.
Yes.
Yes. Okay. Well, that makes sense.
Exactly. If the Fs is twice the Fr, then you get the Dirac belt.
Okay, yeah, because you have the Dirac function, magnetic moment, twice that is the G factor.
Yes.
So they tie that way, even.
Yes, they tie all up. Yeah.
Oh, that's interesting.
Yes.
Okay,
just a moment to find here the.
Don't you also have F4 as 124.7 times 10 to the 18 hertz, which sounds. Is that the same as?
Yes. Actually, this is the annihilation frequency. It's coming out from the Compton wavelength. If you translate it in hertz, it's this kind of frequency. So when two a positron and electron annihilate, they spit out two photons of that wavelength, which is actually also very nice, ties up with the model, and that's actually one also of the reasons I am insisting that believing in my research shows, our research shows, that actually the electron is a spinning twisted photon.
Yeah.
It's not a spin 1, it's spin 0.866 because a normal photon is spin 1h. The electron is a photon 0.866h Planck, which means that it's not a circular loop, it's a twisted loop, and additionally it spins around an axis. So it's a twisted spinning photon. That's all the electron is.
Yeah.
And you can calculate also the energies above from that. But let me please find the Dirac belt trick.
Go ahead.
Yes. Because I have written now 130 papers here, preprints, and I have problem finding the.
I understand. Yeah.
There was in physics world. There was a paper.
Yeah, continue. I'm still I find the. Yeah.
Paper,
you can continue. Still I find the
quantum entangle device. In Germany, they found a device to quantum entangle electron with photon. That's interesting. There's a connection. What you're saying to that somehow.
Can they do that all the time? Like they have a device that just entangles.
Yeah.
Wow.
And the magnetic field is this way. The electron, when it goes there, it produces the photon. So they said they can quantum entangle it.
Yeah, that makes sense.
Yeah, I couldn't go through the whole paper because I'm not able to access that. But I saw the the physics world. So in order to access that, you have to you need a access point. I mean, you have to sign up with them and all that. I have not signed up, but hopefully that paper will come out somewhere. I think that's an interesting thing. What Emmanouil is talking, that electron and photon are photon are intricately related. I mean, they are they are two sides of a same coin, something like that. I mean, according to what Emmanouil is saying.
Which paper are you talking?
There is a physics world. I'm not able to access the chat. I can put that.
I can. Yeah, I mean, but these magazines.
I don't have access to chat
very much. This I like more the. Yeah, because these journalists, sometimes they're misinformed about. I mean, they're doing a good job, but if you don't read the paper, just read the news, the science news, sometimes they're exaggerating some things.
It's some Germany in the Max Planck, some place like that.
Yes.
Yeah, Germany, they conducted this experiment. It's a recent one, like very recent one.
I find the paper. Okay. So Christopher, I suggest you read also this preprint, which is one of the implications of the model.
Yeah.
It has to do with the FSFR times 2 equal 2. It's actually more complicated than we initially thought. It's not that simple, the whole thing. It gets even more complicated about the 4P characteristics.
All right.
So if you go to my research, in research kit with there where it says research menu, or I can send you just the paper to read it. I can send you the paper. So it's this preprint, and of course it gets very complicated. So it is 2. It is 2, but it's not 2. You have to read it. It's not now the time to explain it.
Yeah, I'll read that.
Also, John, if you want to read this, I will send you both the link from this preprint, because yes, the FS frequency divided by the FR determines the whole manifold, the whole ripple. What is exactly the shape, the angular momentum, everything. The radius, this ratio of the two frequencies, the circular spin rotation and the twisted revolution rotation, but we have effectively, we have to effectively translate it from circular to twisted. That's why we use the simulation as well. It's 2, yes. Then you get a Dirac belt, but actually it's not 2. It is a relativistic effect. This is investigated in this preprint here. It's very, very complicated. And actually this actually agrees with our research, because if you see the frequencies, the ratio of the simulation is not 2, it's 1.15. If you multiply 1.15 with 0.866, it comes exactly 1. So that means that the rotation is 2p. It's not 4p. And then you say, what the heck is what's going on? And then you discover Thomas precession. It's a relativistic precession effect. And it turns out that in the rest frame of the electron, it's actually 2p. But in the rest frame, in the frame of the lab, you get gamma times 2. It's gamma 2. So you get time dilation, and it showed up like 4p. It's amazing. Yeah, it's amazing.
Well,
you have to read this. Yeah. But no, it's very complicated. So I won't go. It becomes very technical, and I won't go now to this kind of discussion. But you can read it, both John and you.
So it's very interesting.
Yeah, it's crazy, but it's yeah, it's everything. Everything is 0.8 if you multiply, because the simulation gave 1.15 the ratio. So it's not replicating the Dirac belt, which needs 4p. It's like more than 2p. But if you multiply it with 0.866, it gets 1. And then you use Thomas precession, and you transfer, you have Lorentz transformation of 2p to 4p. So I explained this here in this paper. Of course, this of course is theoretical. It's not experimentally verified, but it's very intriguing about the. And the idea is not mine of the Thomas precession. I actually used only the theory of Thomas precession to my model and translated it. The Thomas precession was first. The idea gave me Preston Jean. Do you know him from the research case? Preston Jean. He's a researcher from Australia.
I'm not sure.
Preston Jean.
Yes.
Yeah. He gave me the idea because I had this problem exactly. Because the simulation gave 1.15 and should be 2. But the model does not, it's not consistent anymore if you put 2. So it's consistent with 1.15. But if you multiply, because it's a twisted photon, if you multiply with the angular momentum, which is not 1, it's 0.866 in the Euclidean space, in the 3 dimensions, then you get ratio 1. And when you use then the Thomas precession relativistic effect, you you can explain why this 4p rotation is apparent. It's apparent only the lab frame. But okay, again, it's a theory, yeah?
I wonder, Emmanouil and Christopher, whether it is connected with Dirac strings. Dirac strings and modons. Dirac string.
Oh, yeah.
Is it connected with Dirac strings and modons somehow? The fibering,
The Dirac belt, yes. I can demonstrate it here. So here, Rajan, look here.
Yeah.
So you have here the photon, yes, the twisted photon, 8.66H, which is revolving. That's actually this line here, this fade line. It's revolving and actually spinning and revolving.
Yeah.
So if the ratio is 2, the spin frequencies with the revolution frequencies, spin is twice the frequency of the revolution. It's spinning twice times faster. Then after 2 pi, you see here the Bretzel.
Yeah.
The Bretzel here. This becomes It's not the same with this. Only after 4 pi rotation, they become again identical. It returns in the same phase, the same state.
Topology.
So
Topology.
After 2 pi, it's not this is not the same because this is up and this is down. The loop here is down and this is in the upper part. So these phases are not the same. Only when you go, this is 2 pi rotation. Only when you go 4 pi, then you return to the initial phase.
solid angle.
That's the Dirac belt. That's the characteristic of the electron.
Yeah.
And this was actually measured with neutrons in the lab. So it's peculiar because if you have a ball, you have a point here, and you return it 360 degrees. You expect after 2 pi rotation you will end up here, but that's not the same. That's not the case with the electron. The electron has this characteristic here. Yeah, it rotates on the same face only after 4 pi rotation, and this actually is very nice demonstrated with when you say that the electron is actually a photon, a twisted photon. Our model demonstrates very nicely this characteristic, this 4 pi characteristic. So it's not a ball. That's just the under result. The real electron is just a twisted. Imagine this. You can imagine this like a loop of electromagnetic flux. So our model is not. I don't know. I didn't hear anything from John. I also want to hear about him.
Yeah.
So our model is very physical. We don't say anything, out some exotic matter. No. This is just flux, normal flux. That's why we say that in our model, in our theory, electromagnetic flux is the most important element. It's a distortion of the ether, of the vacuum space. Every time ether is distorted, it manifests like electromagnetic flux. It's like throwing a stone on a pond of water, and you get all these ripples. And every distortion in the ether is manifested as electromagnetic flux. That's why it's the most elementary thing. From electromagnetic flux is everything woven, all the particles, including the photon. So the photon, imagine it like a circular loop. This is we say that it's a loop, nothing from something exotic. No, it's just flux, electromagnetic flux. This also is flux. The ripple is electromagnetic. It's a loop. It's a twisted loop of electromagnetic flux. With the only difference, it's dynamic. It can spin, it can rotate. That's all.
Okay.
The fermions and bosons are they are interconnected. Fermions and bosons.
Yes, everything is. All the fermions have a similar vortex, dipole vortex structure. And actually, the muon, which is exactly, the muon has exactly the same manifold with the electron. Only it is smaller. Because in physics, the higher the mass, the smaller the particle, the cross section.
Yeah.
Because you need more energy to probe it and so on. So it's not the more mass, more volume. No. In particle physics, more mass means smaller cross section, smaller size.
Compressed. It's compressed.
Yes, and that's actually one of the mysteries of particle physics today. How such a relative small energy particle, which is only for 510 kilo electron volts, it's relatively very small to the other particles. How it can be? It has no sides. They cannot measure size. They should be larger. They cannot measure any size. And the answer we believe is because it's elastic. If you put a lot of fields, if you put in an external field, very strong field, or if you accelerate it with high translational speed, then it shrinks. But the thing I didn't mention before, the fine structure constant, the proportion this to this is always fixed. Always. It may shrink, but it shrink homogeneous. So the fine structure constant, which is the radius here of the tube to the radius to the equator, is always fixed. It doesn't change. The only way to change the fine structure constant of the electron is to destroy it with annihilation, with a positron electron annihilation. Of course, then it's destroyed. Then it releases the photon. The photon gets out of the it's stopping. It doesn't spin anymore. It unfolds to a circular loop and flies away. And the radius is the Compton wavelength. So the radius of the loop here, if you open it, is exactly that's what we measure is the Compton wavelength. Yes.
Yeah. And so it's all vibration. It's like vibration going around.
Yes. You can use how they call it vibration. Yeah. Yes, but it's another name. It's a mathematical name. It's called Maybe Christopher can help you. How you call
Also,
it? You can what's called the name of if you make a model with fibers in mathematics it's called vibration, but I
yeah,
can't remember the exact name of
Or like
vibration.
hop vibration or something.
Hop, yeah, exactly.
of vibration.
Hop vibration, yes.
Exactly.
Hop
What Christopher. And also, is it connected to Mobius strip? It almost looks like a
yes,
Mobius strip.
Professor Otto, a German one, he actually cited the paper and he dedicated a whole paragraph for our research. But they told us that it's an important research and it's highly recommended to read it.
Emmanouil, could you could you do us a favor
Yes.
and stop sharing your screen for a second? I just want to see
Yes.
if it helps with the.
Got frozen for a minute. Yeah.
Yeah. My bandwidth is messing up. So there we go. That seems to have done something. Because my chat, like you said, I couldn't access chat or anything.
I cannot access either. Chat.
Right. So I'm not even. Okay. Yes, I can get out of the program now. Okay, sorry. I just wanted to make sure.
So I want to talk also with John a bit. Christopher, have you any other questions?
Yeah, actually, I do have a few more questions. That was very interesting.
Okay.
One point you brought up there that I'm a bit confused on is that the radius of the loop is the Compton radius, I think.
Yes.
But you also say that I might have this wrong. Are you saying that then when you untwist it and it becomes a circle, which is the photon, that then it becomes the Compton wavelength?
Yes.
Okay, that's very good.
But I have to share again. I cannot.
Oh, I think I understand that though. Oh well, unless if you want to share again, go ahead, because I think it just froze and then you can go back. Oh, it has frozen again.
Yeah.
Yeah. See how it goes. If it'll allow you.
John may have some questions. I think John may have
John.
after that.
Yeah. That's a good point. I'd like to hear if John wants to.
Well, no, I'm just listening.
Great.
Hello, John. You are the silent type. I want to hear about you, or what you think about, because I know you have different ideas. So I like very much to. But let's first let me please answer Christopher's question.
Yeah.
And then we can go. So, do you? I share now? No, I don't share.
Do you have? Should have permission, I think. Unless you also. I think the bandwidth might be going for some reason. It was good up until now.
Okay, imagine now. This is the whole the manifold, but the relativistic, the whole electromagnetosphere. Yeah. Of course, there are not only 6 lines. There are infinite lines. You know, it's not just one line here, 10 lines. But these are all made relativistically by this photon ribbon here, which is twisted. So this is a normal photon.
Just interrupt you there quickly, Emmanouil. We can't see what you're looking at. Is that it?
Oh, you can't.
No.
You can't see.
Well, I can't. I can't see it. And
I think it. Yeah, I cannot also see it.
It might have frozen or something. Looks like because I can't access.
Can you see now? Can you see now?
Nope.
Now? You see me?
You were able to share before, same thing.
I might even come back. That might help, will I? I'll see if that helps. How do I? Yeah, okay.
Stop sharing and start sharing. That can help.
Rajan, do you see the
no,
slide?
I cannot see the screen. I don't know whether John can. Can John see it?
So I just then stop it.
I think you were sharing before. It was coming up fine.
Yeah, I don't know what happened now.
Yeah. I think Christopher is going off. He's coming back.
So I close sharing now.
Maybe you can switch off the sharing, come back again. It might help.
Yeah, I closed it. I closed it. I'm not sharing anymore. I closed the sharing.
Christopher come back because he's controlling it. So when he comes back, maybe he can put it on back again,
Ah, yeah, yeah,
and
okay.
then
Yes,
it should work.
yes,
I
yes.
think. Okay. So Emmanouil has stopped sharing. Maybe you can now control it for him to share it.
So I
Christopher.
try again to share now.
Yeah, you're still a presenter, so you should have no problem.
Okay.
No.
No? That's a problem.
Well,
Okay, well,
I left and came back, and it seemed to fix a lot of things on my end. So I don't know. You could try that.
you mean to go out of the meeting and then come again in?
Yeah,
I can try.
yeah.
I can try this.
Okay.
So how you do that? Just
That
hands up.
red one, the red
Hands up.
phone button. The phone
Yeah.
button.
The
Press the
next-
phone button.
He got it. Hopefully, he knows how to get back. Tell him how to leave, but didn't tell him how to come back. That could be a problem. I don't know. I'm sure he knows how to do that. So
It's a hindsight 2020.
yeah, this is always work from the opposite way. He's probably
That's an interesting aspect of time itself.
yeah.
How the time and the event. Our thought and the time. That's next thing I had to think about. It always comes after that. Is there a physics connection to that?
Yeah, it's a great one.
That should be interesting. Yeah, he knows.
I suppose we're recording all of it.
Okay.
Excellent.
Good job. Yeah.
Let's see you again, guys.
Great. Yeah, back again. Back on the saddle.
Is it raining in your place? John, is it raining in your place? I see it's nice. You have nice weather. So
Connecticut? He's in Connecticut. John is in Connecticut.
Connecticut. Okay. But all you guys are very bright. I'm here dark. It's now 12:30, midnight, and I'm still in the lab. Actually, the closing the lab. At 1:00. I must leave because the closing. I'm not allowed to be anymore here.
Okay.
I know the
John.
class.
Yeah.
So yes, let's try again.
Great.
So John, is it raining there in Connecticut?
There, it's working now.
So it's like a matter of resetting.
Yeah, I've got some noise in the background.
Okay, I couldn't hear it at all. I'm surprised they're able to figure out it's raining in Connecticut from where they are. It's a good deduction.
So, okay, topologically, a spin 1 photon is a perfect circle. Topologically, yes. Forget now. It's even better, not just topology, because topologically is something dynamic. Let's say geometrically. Yes, geometrically is more accurate. So a spin 1, because it produces exactly, a photon produces exactly 1 h bar, the most efficient geometry, which produces the highest angular momentum, is a circular rotation. Any other trajectory for the given radius and the tangential velocity will produce less angular momentum. Okay? So a photon, a spin 1 photon, is geometrically a distortion which is it's a circle. Imagine it is like you throw, as I said before, a stone in a calm water in the pond, and that makes a circular wave which expands, whatever. Yeah.
Yeah.
So we know that the electron has not 1 h; it has less angular momentum, and the angular momentum is square 3 divided by 2. So it's if you do the calculation, it's 0.866 amplitude Planck constant. So now, because this is twisted, Okay, this is the photon, and it revolves very fast and actually and spins also. And this relativistic motion creates the charge. And you know, when you say the word charge, I'm charging. It's something about motion. Yeah, it's kinetic energy actually.
Yeah.
Momentum. It's I don't know. So it's very nice you have the word charge because that's exactly what the photon is doing here. The photon is charging. It's revolving and spinning, and it's creating the whole electromagnetosphere of the manifold, the charge of the electron. And this then interacts with the environment and creates the electric field as a pressure. And here, where you have the dipole vortex join, you have the dipole moment. And when you see also the animation here, you get the lines coming out from the North Pole and going to the South Pole.
Yeah.
But this is actually a convention. But it was nice that we can that the manifold turned also this future also. You can see clearly that the lines are going from. If you look more closer, the lines here. Uh, okay, you see here's the North Pole. So the lines flowing from outside, coming inside, and they're making this revolution here. So the North Pole, as we know, the flux lines going out and coming into the South Pole. So the macroscopic field has this inherent future from the actual charge. The charge is doing also the same. This vortex, this type of vortex, which also you can do that in nature, you can find it, has a flow. It has a unidirectional flow. Doesn't the energy does not meet here? You know, you get here is a tube. You get the flux transferring all the time, inside out, inside out.
Okay,
So
Emmanouil.
the question to answer the question now, to answer the question, when an electron within a positron annihilates, this here ribbon breaks out and unfolds back to a circular loop. What the Compton wavelength represents is the perimeter of the loop. When do you remember that the reduced Compton wavelength, which is this symbol here with a dash, is what is the Compton wavelength divided by 2 pi. So it's a radius.
Yeah.
It means that this here, since this here gives it's divided by 2 pi, this here must be the perimeter. So the perimeter of the loop is the Compton wavelength, which is 2.42 power 10 power of minus 12 meters, and the reduced Compton wavelength is the radius. Yes, which is 3.86. If you do the calculation, it's 3.86 times minus 13 meters, because the radius is not 2 pi r, it's just r now. So that's very essential for the theory. But if you just ask this, that's actually, it's called the Compton radius. This electron, which has the Compton radius, is the only, there where classical physics are stopping, yes, which allows to get the magnetic moment with a tangential speed c. If you reduce the Compton radius, you make it smaller, then you have to go to superluminous velocities, tangential velocities, in order to get the given value for magnetic moment, you know. And this is not allowed, as you know. So this is the minimum radius, the minimum allowed radius to be consistent, the model. And it's called also Compton. Compton electron, but of course Compton gave it just a sphere. That's he never gave the report. That's our model, yeah.
Okay, well, I'm a bit. I'm
so
still
this is
confused.
This is the physical meaning on all.
When you say perimeter of the ribbon, do you mean like the length of the ribbon as it's?
Yes. Yeah, if you cut the length.
Yeah.
The Compton wavelength is the if you go review again what is the Compton wavelength, it's an effective value. It represents the energy of an electron when it's converted to a photon. It's effective. It's the equivalent energy of the electron when it's converted to a photon. That's the definition of the Compton wavelength.
Yeah, I understand.
So when you turn an electron to a photon, which this happens with a positron-electron pair annihilation, it produces two photons. When you measure the wavelength of this, decayed photon, it's exactly the Compton wavelength. That's why we're telling also that our model is consistent with this. So when the two electron and positron hit together, this the photon electron twisted this ripple gets knocked out from the volume here. It loses momentum. It stops spinning, and then it unfolds and travels translates and this here the perimeter again. Here is the Compton wavelength with the radius that reduced Compton wavelength.
Okay, but then how can you say that the which is a very interesting result that I want to get onto next, is the fine structure constant being part of the so it's like the diameter or the radius or the diameter of the inner tube by the diameter of the whole thing.
Yes, Christopher, because we examined the end product.
Right, you're opening
the relativistic effect, the end product. We don't examine this.
Right, so you're unwrapping that thing, and then so really you're measuring. It's the difference between the inner and the boson, the photon.
Yes.
Ah, okay, interesting. That makes sense, because I mean, is it one way of saying the fine structure constant is to say the elementary charge divided by the speed of light, but you had a different interpretation, I think. It was the radius by the Compton, or divided by the Compton diameter, or
I can show you again the
okay, yeah. Well, I suppose that's very interesting. I find that all very compelling and quick and very convincing. I like the way everything fits together.
Yes, it ties all up. I mean, that doesn't mean that it's correct.
No,
but it's. I think it's a honest try to decode the possible intrinsic mechanics of the electron, which I believe are deterministic.
Yeah,
that's my
right.
I believe they're deterministic.
Fascinating.
So yes, it ties all up and it comes down here. This is the first geometric physical explanation of the origin of the fine structure constant, and it was actually always in our face, because this is not my relation. It's in the literature, but we never we don't know the geometric, the physical meaning of this. What does this mean? Yeah. So what? So we don't combine this equation here in a manifold. So this explains everything. You have here the classical radius. You remember how I started my presentation? Maybe it's all the options together at the same time, because you had options. The options were contradicting. You had the classical radius, which is this radius, is two orders of magnitude smaller. Then we have the Compton radius, which is 2 orders of magnitude larger, and it doesn't fit together. But with this manifold, that was not my initial thinking. I just did the model and then measured the distances and all of that, and came up. So I was also astonished. I never had in mind to decipher the fine structure constant. I just want to make a charge manifold that describes the angular momentum, the magnetic moment, and so on. That was by accident. By accident, hey, this reminds me something, and then I looked up and it's the value of the classical radius. Oh, that's nice. And then I said, Okay, let's now this, and it came up the Compton radius. And then I found also, no, wrong, I didn't find, I just, then you can find in the appendix the analysis. Then I said, let's see what was my initial thinking. I didn't, I found it afterwards. That was just a confirmation of this equation. What we did is to calculate the flux outside here in the sphere and the flux going inside. And I had a hunch, a small hunch, maybe it comes out one divided by 837, which is the fine structure constant. And actually, we did the analytical proof, and the charge here, the outside charge to the charge, the charge inside the whole cube here to the charge outside is this value here, because the radius controls the charge. So it's like water, It's if it's very thin, it's going more. You know what I mean. So the radius controls the ratio is also the ratio of the flux inside to the flux outside. The flux which is going inside the tube to the flux outside is the fine structure constant. And we have this analytical proof in here by this novel equation. These are in Weber units. Actually, this is the dipole charge in ampere meter units, and you just put the permeability of free space to turn it into Weber units. And this also is the the value of the flux quantum to find the superconductors. So if you do this, the same ratio comes, the same value, the fine structure constant value comes out. And then we found this equation here. Okay, then everything ties up. Fine structure constant, anomalous magnetic moment, classical radius, charge radius. So the only problem we have is it's big. Yeah, it's big. It's minus 13 meters. And they say in the experiments they cannot find they put the upper limit at minus 18 meters. So it's big. But the paper now we are writing, I believe it will go out in a month or so. We explain why the possible reasons are for this. So the first reason is that this little bugger here, the electron, is elastic like hell. It has actually in the literature, it has elastic scattering. So if you try to bombard it with a photon and it's free, it flies away. You cannot get the measurement by photons. The other thing is that what we believe that when it's accelerated, it shrinks altogether, but homogeneously. The fine structure constant is maintained. It doesn't lose the fine structure constant, but altogether it shrinks. And the faster the translational speed, the smaller it shrinks. That's another possibility. The other possibility, which is very possible, is because this is anisotropic, yes? You cannot characterize this flow of energy as isotropic. But this is the charge creates this here is the near field. It creates the far field, the far electric field and magnetic field. You know the definition of the far field. You can yes, because I also even didn't know that when I have learned it now.
Right.
So the far field is something different. Has something to do with the wavelength. It must be I think at least 5 times the wavelength, the Compton wavelength.
Yeah.
The measurement organ, the measurement apparatus must be at least twice or to 5 times farther away to measure the far field. If you go to the near field and try to measure this, you knock it down. You knock it up. So you can't go very close to the charge. You measure only the interaction fields, but the interaction fields E and M are not the charge. The interaction fields are going this way. It's like a pressure. You have a ball inside water. You try to turn it, it will create a pressure outside. And if it has also 2 holes, it will create a vortex here. So what we think also it's possible that this little bugger creates a totally isotropic far field. So you have here, for example, that's sorry. Yeah. So this is an example from nature. This are actually is the flat version of our model. These are called modons, are two vortices which are opposite speed direction. And when you put food coloring, they connect with a tube. So it's the 2D flat version of our version is coaxial in 3D, but this is flat 2D.
Yeah.
So you see here, you have the vortices which are anisotropic fields. You can call them anisotropic. But here, they create, this is the analogous of the E field, the interaction field. You see here it's totally spherical. So it's possible in an isotropic field to create an anisotropic near field to create an isotropic far field. So this is the far field.
Sure.
So this, and here, if you can see also the flow if you observe very closely.
Yeah, were you saying that the in the green box there? I thought you mentioned earlier that that was a spherical wavefront, and I just don't see that as totally spherical. Though it looks more elliptical, but I don't know if that's important, really.
Yes.
Okay.
What happened?
I'm not sure.
So you can see also the lines.
Yeah.
It's also the magnetic moment here. There's a flow also here between. This represents the magnetic moment, and this here is the electric field. Yeah.
Oh, okay.
So yeah, it's not spherical, of course. It's not full spherical.
Yeah.
Yeah, that's why also but it can create a spherical interaction field. I mean, you can have something. You can have even a plate. If you spin it not on its axis, its longitudinal axis, it will create it's anisotropic, or it will create an isotropic interaction field around. Yeah, if you have a plate and you spin it inside the water, say not on its perpendicular axis, but on its parallel axis, like flipping a plate like this. So it will create an isotropic field.
Okay.
Yes. So.
Yeah.
So yeah, of course, it's not. That's also was our suggestion that they should not measure just here, for an anisotropy. They should measure this compared to the rest here, because this is not spherical. It's missing a small. This actually is the anomalous magnetic moment.
So if they were to do that and they were to find, well, they would have to increase their accuracy. But if they were to find it, then that would be proof of the theory, and if not, it would disprove the theory.
Yes, it's a prediction. Yes, it's a prediction. Our theory does.
That's cool.
But yes, but it's not absolute prediction, because also our model predicts that it's possible in an isotropic charge to generate a totally an isotropic interaction field in the far field.
Are you saying that it would look spherical or something?
Yes, I mean it could be, as I showed here before, even if it's anisotropic. It's not a perfect sphere. It's missing here. That it's not 2 pi r. It's missing here the classical radius. But it could produce a far field. You have to go near to the near field to see any anisotropy. That's also a problem.
Okay.
But it's actually a prediction. Look, our prediction is that the anisotropy is between the pole and the equator, not between the two poles. Between the two poles, they're perfect. They also it's a defect, but it's it's an equal defect, because the dipole moment measures between 2 points any difference. There's no difference in the amplitude. So we say no. You should not measure just in the spin axis. You should measure each pole to the rest to see the sphericity. And that's why we are suggesting here an experiment for that. And we predict that the anisotropy is this value here. Yes, 18.2 power of minus 15 centimeters. So it's in the order of minus 17 meters, the anisotropy. But that's the nice thing here, that the sensitivity of the experiments, the currents, are much more than what we're suggesting. They're looking for minus 30 centimeters for an anisotropy, and they cannot still find any. And that's why they have In nature, the articles, the electron is perfect spherical, the electron charge. But they don't actually measure the charge. They measure the far field. They can never measure the near field. It's a problem.
Yeah.
And actually, they're using also cyclotrons. For the magnetic dipole moment, they're using cyclotrons, which are accelerating the electrons very close to the speed of light. And according to our model, it shrinks when it's accelerated. Yeah, that's all. So we tell this guy, no, don't measure this between the here and here, not between here and here. And when you do that, then yes, you will discover our prediction. If yes, it's a big if, which is in the order of 18.2 point. What is it? I'm a bit sleepy now.
It's okay.
Yeah, it's I lost it. It's 18.2 whatever. Minus 15. Yeah. Yes. Here. No, lost it again. I don't know.
Well, I tell you what. I'd like to share something. Just more of a comment, really, on your work rather than a question.
Yes.
If I could share my screen.
Yes, of course.
Okay, cool. So there's a few things. I found this place called Physics Detective. I don't know if you know him. He's quite. He wrote a blog basically online. There it is, the Physics Detective. And if you go down here, he's talking about an old theory that was kind of big and important before maybe string theory came along, and it's very similar to what you're talking about. But it's dealing more with the proton.
Oh yes, I've seen this. Yes,
yeah,
I've seen this article. Yes,
cool. It's an old idea, but that it started coming back into fashion. I really like this because this is a photon twisted into the proton. So that's very similar.
Okay, but Christopher, if you see this was a knot. Our model is an anode. It's not a knot. This is a knot. It's a how you call it, a triple. It's a knot. Our model is not a knot. It's an anode. It's not zero. It doesn't tie up. It doesn't get tangled. It always untangles.
Oh, okay.
Yes.
Interesting. You'd have to show me that. Maybe if you knew of a graphic visualization that could. It'd be interesting to. I'd be interested to see that.
Yes.
Video. It shows in the video. In his video, it shows.
No, I don't think so.
You can see the animation with a ribbon. With a ribbon, it's an anode. It never ties up. It always it's loose.
Oh, okay. So are you saying that the shape that you've been showing throughout the talk that's able to kind of wind around is the same topology for the proton?
It's called anode. It's not zero. If you put in Wikipedia anode, you will see it's a loop which it's actually a circular loop.
Okay.
A circular loop is an anode, but our model is a twisted loop, but it never tangles up. It never, it doesn't make a knot. And you can see that very clearly here. I don't know. Can I share?
Yeah, there's just one other thing that I'll show quickly because these were just small comments. There's this research that was done, I guess, in the 18th century or maybe 1900. Lord
Kelvin first talked about atoms as vortices. It's the vortex atom is called. Lord Kelvin, yeah.
Okay, well this is slightly maybe more I don't know, left field or something. It's like the occult chemistry, clairvoyant magnification into the structure of atoms, periodic tables, and compounds.
Yes.
So back in the day, they were trying to use psychic powers to see into the atom to see what it looked like, and they got these winding structures, which I thought were very similar to what.
Can you send me please this link? This link, I'm not aware about this.
Okay, well, all I did was search clairvoyance on atoms, and that's that's the list of images you get, the results, and then you can go into like occult atoms here.
Direct observation.
I can send you that link in chat. That's Yale University.
Okay.
And you can see occult chemists here. Those guys look pretty cool.
So yes, actually, if you want the whole history, Lord Kelvin imagined the molecules and atoms like vortices. He was the first, I believe. Actually, in Wikipedia, if you say molecular atom vortices, it will come up in Wikipedia. And there is also the toroidal model of the electron, which was first. But this guy just imagined the electron like a ring, just not so complex as our model. So I can actually let's look
Yeah,
toroidal model of
sure there.
electron.
So there
Toroidal.
some interesting diagrams on this. I'll have to read that again. I can share that. I'll just share that with you in the chat, and I will stop
Okay.
sharing my screen so you can take over
Yeah,
there.
we cannot access chat here. I cannot. Access.
I had a problem earlier. It sorted itself out when I left and came back, but you're not blocked or anything, Rajan. So, but I can make you a presenter just in case it helps.
Oh, to
Christopher.
be presenter, you have to be a presenter too.
I don't think so, but try that. Try it now.
Christopher.
Yeah.
Okay, you can look up on Wikipedia. It's called toroidal ring model.
Okay.
So it was first suggested by where's the guy? Theory history. Okay, for my bear first, of course. For my bear. You know the ring of current that produce. But I think there was another guy. Ah, yes, it's called Parson. It's called Parson magneton. Maybe John knows about it. It is a model of the electron where the electron is margined like a toroidal ring, like a toroidal ring. It's actually very interesting. Yes. And the other guy, so you search toroidal ring model in Wikipedia.
Yeah.
And the other Wikipedia reference, where you can also find the other references, the actual reference in the literature, is I believe it's called Lord vortex atoms. Vortex atoms.
I think I have seen the proton version that is wrapped around a torus. It's like a trefoil knot, but
Yes.
around a torus. So it's
Yes.
not actually a knot. It's more of a
Okay.
loop.
So the other
This is
theory
what I was
is called vortex. It's called vortex theory of the atom. You can find it. You can find it in Wikipedia.
Mm.
It's developed by first attempt 19th century by William Thomson, later Lord Kelvin. It's called vortex theory of the atom. If you type that in Wikipedia, you will see the article. So these were actually the pioneers, Lord Kelvin and Ampere, which imagined the electron being a kind of ring, kind of vortex ring, like a smoke ring.
Yeah, I mean, even that concept is actually still quite in favor today, even among conventional physics, because it's all about wave function, and they like to imagine it as like a river, and then you have eddies, and sometimes you have vortices and such like that. So I think it seems like it's a very promising idea. It's very interesting, and like you said, the two vortices connected by that's like a mainstream theory as well, or at least it was back in the 90s.
It could be modons, right? Modons connect them.
And you don't have to think complicated. You have the solenoid. The solenoid has spirals and has inside straight flux. It's homogeneous. So why the electron should be any different? The electron is a sphere, so it must have the flux must going as spirals on a sphere, and it has also a magnetic moment going through the poles of the sphere. Why should it be any different?
Right, but there's one issue though, isn't there?
Yes.
Or maybe it is not an issue to you. It depends. So in some sense, earlier you were talking about, Emmanouil, about how the particle is less fundamental than the field or something, and that so it's like the vortex. It's like an ether field that's vortexing in and then creating the particle rather than the other way around, which makes sense. But I do believe like that the current thinking from at least the mathematical side is that and relativistic side is that the particle is more fundamental. It's just a hunch I think they have. But also your theory would suggest more that like all particles are sort of like at the whim of this much larger field, like a river. So everything's just like flowing down a river or something.
Yes.
So there's this flow, and it's like I don't know. It could have maybe metaphysical problems with it.
Look, yes,
Interesting.
okay. I don't know. I believe that the vacuum space is not what we believe it is.
Oh yeah.
I think it's a medium. It's some kind of material. It has all the characteristics.
Plenum. That's what I say.
I don't know. Maybe, but it's even the very progressive big names in condensed matter and also particle physicists, like Wilczek, the Nobelist. I can send you also his lecture. Believes okay, it's not the ether. He actually says that he was interviewed, and he says no, the ether is real. He on stage in public, but it's not the ether what was thought before 200 years. It's a more an ether which obeys the Maxwell equations, but it's a medium. It's a really it's a vacuum. There's nothing like nothing. There's something always there.
Oh yeah.
It's not epistemological to say nothing. There's no nothing. Maybe there's nothing. There's a void of some substance, but there's no void of all substances. That's not possible.
But if you think about it, though, if you're saying that the particle is secondary to the vortex, which is secondary to the greater medium, then in a sense you're saying
not to the vortex. What makes the flux line? You know, the flux line. This is accepted by the mainstream theory. The flux line is made out of virtual photons. They don't know what this virtual photon. They calculate the mass. They calculate the mass. They don't know. So the virtual photon, it's a photon. So it's an elementary particle.
Yes.
I say, that's the definition. The definition of the magnetic or electric flux is that it's a stream, a coherent stream of virtual photons. You can find it out. It's a coherent stream of virtual photons. It's not something I invented out.
No, but that would suggest that the particle is more fundamental than the vortex.
Yeah, the photon, the virtual photon, but they don't know what the virtual photon is.
So who knows what that could be?
It calculates only the mass, but they never saw what a virtual photon is, or what is never measured it and never observed it.
Okay.
But the math say that it's there.
Yeah.
So that's why I'm telling that the flux is more important. It's a distortion in the space-time itself.
Yeah. Interesting.
So the flux makes the electron. That's in order to understand our theory. That's important. Our theory says no. The flux is more like a distortion in space-time, since it consists from virtual photons. So it's a more important. Yeah, you can say that the virtual photon is more elementary than the other particles. Yeah, okay. But all this effectively makes a twisted photon. So forget about you can forget all this stuff about the flux. And you say it's just a photon that, look, it's twisted. It has a spin 8.6 as given by literature, and also spins around an axis, and that makes the electron. So essentially, you can say that it's a photon, a twisted photon which spins. And that actually shows the experiment, because the experiment shows when two electron and positron, when a positron and electron annihilates, which is the positron is the anti-electron. It just has different. It's an electron with opposite charge. Yeah. When the two bump together, boing, the two photons come out, and each photon has exactly the Compton wavelength. So what tells you this? What you imply from this?
Yeah.
So it's possible that the photon ribbon is entangled there, spins what makes its job. When it crashes with another positron, it flies away, it stops spinning, entangles, and flies away, like a normal photon.
Interesting.
Yeah.
I wonder, is there any, do you think there's any, like, practical application to this on
Yes.
Research, or is it more just filling out our gaps in scientific knowledge?
Yes. There is application.
Yeah, cool.
Yes, I believe that this is the key. Do you know Star Trek?
Yeah, of course. He doesn't.
Okay, it's the replicator.
Oh, nice. All right.
You can make matter photons to matter and so on. Because what you actually do, you convert a boson to a fermion. Yes.
Yeah. Cool.
Also, this you can also match it with string theory. In string theory, all fermions are open loops.
Yeah.
Yes, but mine is a closed loop. So why it's not consistent with string theory?
Oh, that's weird.
No, it is consistent because I'm talking that it's a boson. So in string theory, a boson is a closed loop. So mine electron is a boson. It's just a twisted loop. So it's consistent. It's consistent also with string theory.
You have to explain that again. Maybe explain that to me again.
Okay, in string theory,
loop it's not open, right? So
yeah, in string theory, the fermions are represented with an open loop. So just a vibrating string, you know.
Yes, sir.
All the bosons, like you know, photons are closed loops in string theory.
Okay.
So one could say, you know, it's your model is not consistent with string theory because you represent your fermion as a closed loop. It should be an open loop. Yes, but I'm telling that actually the electron is a boson. The fermion is a boson. It's just a deformed boson.
I guess you.
Yeah, you know.
So it's consistent.
Yeah, it's a deformed spinning boson.
Oh, that's really cool. Yeah, so the future could be really interesting, but you'd have to get down to that size and twist it. And
yes, but now you can find also sushi, the supersymmetry, the particles. You know, the supersymmetry theory, the supersymmetrical theory says that every particle has every fermion has his boson, and every boson has his fermion.
Yeah.
They are both inside inside one. There's the same thing.
Yeah.
They're hidden inside. They're both bosons and fermions. That's the nice thing.
Photoelectric effect.
Yeah, so that's why the decay they become from you can't have from bosons with the electroweak. You can have all these transformations are the electroweak interaction. So you can have bosons. You can get from bosons electrons, and you can get from bosons fermions or from fermions bosons because they're the same thing in the same
X-ray. Yeah. The X-ray
the same thing in the same package. Yeah.
Electrons and photons come together in the X-ray, right?
Yes. It's the same thing it's a different facet of the same coin. You take a boson, you twist it, and you make it a fermion. And you take the fermion, you untwist it, you break its spin, and you make it a boson.
Cool. I wonder, John, then, do you see any contradiction or connection between your theory and this one? Because I see like the vortices, you know, as like a sink and a source, but within each atom.
Micro black hole and micro wormhole, micro white hole.
Yeah, this is what you've been talking about for months, Rajan. I get a much better picture of it now, so it's interesting.
Yeah, John. Yeah, John's
comment. If there is a connection, it's with the vortices.
Right. Yeah.
My model has the electric charge being a vortice, but there are two different types of vortice. One is the cyclone type, and the other is the smoke ring type.
And okay, and how does that? How would you envisage that? Do you think that there would be therefore two different types of fermion or something? I don't know.
Well, the particle in my model is a magnet or an assembly of magnets. And as they move, they produce vortices. And that vortice then is the electric charge.
Yeah.
Charge is not intrinsic to an electron or a proton. See, they can't be. See, Emmanouil has the electric charge being what? On the surface? But he pointed out the prime problem right in the beginning. That is, if the electron is going to be charges on the surface of an electron, then they're going to repel. And there's no mechanism to keep them together.
Yeah, but my model, the charge is not charge, it's just flux. The charge is flux. The flux makes the charge, not the charge of flux. That's I told that from the beginning, that it's very elementary to our theory, that the flux is a priori of the charge, not the charge a priori of the flux. That's just my model. Yeah, it works out for me that way.
Yeah, I think I understood that.
Mm-hmm. You're right. Yeah, John, you're absolutely right. Yeah, that's a very good observation. But my argument for that is that in my model the flux is more important, it's prior to the charge, as a distortion of space-time. Space-time. It's a manifestation whenever the space-time is distorted, it manifests the flux, which is this virtual photon thing, the virtual photon that come out of the flux. So in the beginning, in the Big Bang, I don't know whatever it is, you have a very homogeneous fluid, if you can call it a fluid, and then there were some differences, small differences, that created the vortices. And when two different spin vortices come close together, they create this loop. This is an established phenomenon. It's called modern. You can check it in hydrodynamics. So they established this tube. So maybe then they came together, the two magnetic monopoles, which is actually direct monopole, and they formed the fermions. So all the fermions must be dipole vortices of flux. So that's my theory.
Yeah, that's an interesting concept of where all the magnetic monopoles are. They should be there. They're lost. So they're.
But John is correct about this observation. Yeah.
Yeah, interesting.
Yes.
I missed that. Sorry, John. I had to fiddle configure with stuff when I was in it.
Yeah, the Dirac string. Each of the monopoles will have a Dirac string, right?
Yeah, Dirac string. That's what I discovered that 2 years ago. I thought that Dirac thought, even Dirac never talked about. He didn't believe that monopoles are just isolated. No, Dirac says in his theory, yes, you have a monopole and an anti-monopole, but they are connected with an infinite thin Dirac string. So even Dirac admits that there cannot be an isolated monopole in nature. It's always a dipole. It's the nature of magnetism. Yeah. So
but in superluminous, like dark matter, it could be just monopoles going around.
Yeah, okay, that's an hypothesis. That was also in our paper.
And they come together and they form horde, like what John is saying.
Yes, maybe. When they come out from the superluminous phase, yes.
Yeah. And the Dirac string of the North Pole and the Dirac string of the South Pole, they come together and they join together, and then they form the dipole.
Dirac string, yes. But in cosmology, the cosmology say there's no the energy is the same. So no new matter, no new energy was created. It's the same from the Big Bang. So all the electrons were created then are now. They're only decaying into other things, but the energy is the same. There's no new energy created in the. But again, now with the expansion of how they called it, the expansion of accelerated expansion, the dark energy. Now it seems that the energy is increasing. So what's going on?
Yeah,
it's a problem.
I think there's a leak. My feeling, like I was talking with Christopher earlier, the universe coming like that, but there is a leak that leaks into the other
some kind
part.
of refresh. Yeah, some refresh.
Yeah,
Maybe
that's why
action, yes.
everything changes. Fine construct fine structure constant, everything, and the uh, even Planck's constant, everything will change over time because over a period of time there is a leak between the real
Yes.
observable universe and the
If you ask, this, which are talking about the vacuum space and the 0 points, it seems to me that a pot with water, which it starts boiling, so it spits out, the small amounts of water when the water is boiling on the surface, bubbles and so on. So that's the picture we have now for the vacuum space. It's something like boiling. So I believe there is what we don't perceive like empty is actually a different phase of matter.
Yeah.
Like like ice, vapor, and solid.
Yeah.
Maybe it's some kind of exotic phase that we are out of phase. So we
Yes.
perceive it like empty, and that's why we wrote the paper with Rajan. Actually, Rajan wrote the most paper. My contribution was very small in this paper, and maybe it's superluminous. Why not? Maybe it's some kind of superluminous phase of matter. I mean, imagine a Brownian motion, but now the vibration is becoming superluminous. And when it becomes superluminous, it's imperceptible from our space-time domain. We're out of phase. We cannot see it.
Yeah.
And even John will agree. I mean, John is more valid to say about this. He knows about more things about this. If you take Maxwell theory and take the permeability and permittivity of free space, these are characteristics of a medium. Yeah, John. So even these two values, the permeability of free, mu zero, and e zero. What is this?
Yeah, exactly. Yeah,
Which gives, when you divide the square root, is the speed of light. It's actually, they say in Maxwell theory, I think permittivity is the elasticity. You call permittivity the elasticity of a space, and permeability, he called it I don't know,
a different term.
something the stiffness. No, that's not stiffness.
stiffness.
So even Maxwell is strongly infers that actually vacuum space is a medium.
Yeah.
Well, he believed in vortex theory. Actually, Maxwell initially was talking about vortex theory. Then he moved away from it to some people.
Well, yeah, you can imagine Maxwell with the whole like vortex rotation and then the forward.
He talks about that, like vortex pools, and then he calculates the hydrodynamics.
So this is, look here. This here is a fermion, yeah? It's a
Oh.
Now it's a photon. Now it's a boson.
Yeah.
Here is a fermion, and now it becomes a boson.
Yeah, that's good. I like that. It's a bit like a slinky, that thing.
Yeah,
it's a gadget. It's called Toroflux. You can buy it.
All right.
Yeah, it's in eBay, wherever. Toroflux.
Great.
What is it called? Toroflux.
Toroflux. It's
Toroflux.
it's you can also if you put it in your hand.
Oh yeah. Cool.
Oh yeah. Or you can go from one hand to the other hand.
Yes, but I don't have.
What? Oh yeah. Thing that's deadly. Yeah. That's great.
Yeah.
Class. I might get one of those after that demonstration. Yeah.
Yeah, it's relaxing. You can put that to here.
It's worth its halo. Good.
The Electron is very relaxing.
Yeah. That's good.
No, I think that the electron you mentioned is a compressed field. So, in vacuum, it is expanded field. I think that's the difference.
Yeah, yes. I don't
It's a
know.
compression versus expansion, I think. So that's all it
I
is.
believe
And
that
the
it's
vibration.
elastic. It's elastic.
Yeah, and the
The
vibration,
elastic pattern, like,
stiffness, that's it.
yeah.
Vibration, stiffness, elasticity, and compression and expansion.
Yes.
I think
And all
that,
this, you actually must know better. This characteristic, the elasticity and the stiffness or whatever, dictates the propagation of a distortion inside the medium,
yeah,
right?
yeah,
So the speed of light is the reciprocal of the square root
yeah,
of mu zero times E zero. Yeah. So everything indicates that it's a medium. So it's not empty. Yeah, yeah, of course it's empty from baryonic. If you go to free space, into vacuum space, of course it's empty of baryonic matter. Baryonic matter. But it's not empty for everything. There's no absolute void. That's why.
yeah,
That's one point. It's not only maybe. That's my hunch. Inside a black hole, because I don't believe they have found yet non-rotational black holes. All black holes are vortices.
yeah,
The accretion disk. So if you look inside the water and you get a vortex inside the water, the funnel is empty from water.
yeah, yeah.
Maybe there, only inside the black hole, it's totally void.
Vacuum.
Maybe there only. I mean,
Only
even
the
void
vacuum. So
from the
vacuum is
also the ether is missing.
Yeah.
vacuum is dynamic.
Sorry.
So it's a dynamically vacuum exists only in dynamic situation. Dynamically only it happens. It's not static.
Yeah, dynamically, yes, of course, yes. It has, if it was a non-rotational black hole, but then they cannot find any non-rotational. They're all rotational, as far as I know.
That makes
Yes,
sense.
then the vortex theory collapses. But I believe I have also written a paper in the research chat. I believe a question. I made a question. Maybe black holes are not made from an imploding mass, but they're just defects in the space-time itself, the fabric of space-time.
Yeah.
Yeah.
They're just
Like
there, they're
fluid.
like a cheese which has holes. There's defects of the fabric of space-time. And
That fits in with John's theory, I think, as well. Okay? Just as a geometry.
No. Yeah. I think if you spin fluid very, very fast, you can create a vacuum inside.
yes,
So it's a fast rotating thing, space, the local space time.
the
If it
funnel
rotates that
is
fast,
empty. There's empty of water. There's no water. If you make
yeah,
like this, the funnel of the vortex, the eye of the vortex, is empty. Just air. It's no
yeah,
water. So
yeah,
maybe there's also a hole in the space-time. Not,
yeah,
and you can easily disprove this. This is falsifiable. The hypothesis just made is falsifiable. They just have to look on the sky to observe a supernova and then come back 2-3 years and find the same spot where the supernova became a black hole there. If they have this observation, then this theory is you can falsify it.
Yeah.
But there's not yet. They have not yet this kind of observation.
I think a vacuum is an interface also. Like you have superluminous thing and you have a matter. So between that, the vacuum is inside here. Between a phase.
Yeah.
It's a phase between superluminous and matter space. It's a phase. Like we saying multi-phase. So you have superluminous phase, then you have the particle phase or the matter phase, and vacuum is in between.
It's in layers, but it's everywhere, not just layers.
Everywhere. Yeah.
It's everywhere.
Yeah, if you talk about flat space, if you project to a flat space, you get like that. But then if you project to Euclidean 3D space,
Yes.
then you get by rotation, like you said, the hole.
So
you create a hole inside. That hole is what is a vacuum. There's nothing inside that hole, so it becomes a vacuum. But in that hole, particles can splash into it. Like spatter into it. That's why you see they say in vacuum the particles will evaporate or it'll pop out because of this reason. Because it's dynamic. The vacuum
Okay.
doesn't exist statically; it is dynamic. So that kind of indirectly gives evidence that that inside a black hole is totally vacuum, probably.
Yeah,
It's very
maybe
vacuum,
it's
so it sucks everything in. It sucks everything,
Yeah, yeah.
light, everything.
Very good.